So welcome to everybody to the Gaseous Detector session. Our second convener is Maxim Tito, that unfortunately cannot be here in presence today, but fortunately is connected remotely. Hi, Maxim.
Hello to everyone.
So I think it's better to start because today the session is really crowded. We will have 9 talks and 40 posters. So first speaker is Christian, that will speak about the Alice TPC chamber that has been refurbished during LS2. Thanks.
Yes, thank you very much. Thanks to the organizers. This has been a very nice conference so far. I'm very happy to be here. Thanks also to all of you that got up early after the social dinner. So let's look at the slides, please. I'll start with some sentences about ALICE in general. So ALICE is the dedicated heavy ion experiment at the CERN LHC. And there are a few distinct differences if you compare ALICE, for example, to ATLAS and CMS. So we are optimized for heavy ion collisions, which are usually lead-lead collisions. And those we get at a much lower rate compared to proton-proton collisions. It's usually in the few kilohertz range, and after the upgrade to about 50 kilohertz. And so we have lower collision rates, but we have much higher track density for each collision. So we have up to 20,000 tracks or even more for a collision. So consequently, our experiment is a bit different than the others. And the main difference is that we have a time projection chamber, or one of the differences, let's say like this. This is an event display from Run 2. This is a xenon-xenon collision that we had in 2017. And you appreciate the number of tracks. This has been just one interaction, and you get lots of tracks. And in the past, ALICE was running in a triggered mode, so we were triggering on these collisions. We were selecting, for example, central heavy ion collisions, and then reading the detectors based on that. The TPC, as I said, is one of the main detectors in ALICE. It provides tracking and also particle identification. It's about 5 meters long, 5 meters diameter, and it's basically a cylinder, as you see. It has a central drift electrode that divides the drift region in 2 halves, and then the electrons from ionization, they drift up to 2.5 meters to the end plates where the readout chambers are situated. Each of the end plates is subdivided into 18 sectors, and the sectors are subdivided into a small inner readout chamber and a larger outer readout chamber. The electron drift time, this is maybe important to know, is about 100 microseconds. So a TPC is rather slow. You basically integrate everything over 100 microseconds, which means as the collision rates go up, you get more and more pile-up very quickly. So as I said, in the past we were triggering, we were using multi-wire proportional chambers, and that was until 2018, until the end of Run 2. In the future we have now, the future is starting now, we have new requirements. We want to read basically all minimum bias collisions, not only central or semi-central collisions. And we want also to increase the collision rate. And in order to do that, a gated TPC readout, as it was usually done in the past, does not work anymore because it would be very inefficient. And we have to go to continuous readout. So we read out the TPC all the time. But then you have the problem that you have some ion backflow, which creates space charge in the drift volume. And space charge then distorts the drifting tracks, which makes the performance suffer. So we need to minimize the ion backflow in a different way without the use of a gating grid. This is just showing you how data taking in the future will look like. So basically we are not taking individual pictures of collisions anymore, but we record a movie. So we just record a continuous stream of overlapping heavy ion collisions. These are our readout chambers. I assume that this audience knows what a gem is, so I will not explain that. We have 4 gem foils on top of each others. The larger outer readout chambers have 3 stacks of gem foils, and the smaller inner readout chambers have 1 stack of gem foils. This is the gem stack shown schematically. The first layer and the last layer are standard gem foils, while the 2 in the middle are large pitch foils, so that you see that the holes are spaced wider. In addition, we use a highly optimized high voltage setting that is a bit different from the standard settings. And with this, we can achieve this performance. So on the x-axis, you have the ion backflow, and you see that we reach 1% of ion backflow. That means 1% of the ions that are created in the chambers in the stack can escape into the drift volume. And you also see that there's actually a compromise. So the better the ion backflow gets, the worse the energy resolution is. But with the TPC, of course, you also want to measure the energy of the ionization. You want to do particle identification based on that. So we have to find a compromise. And this green region was the region where we were aiming. This is our requirement. And you see that there are basically a lot of settings fulfilling that. This shows how we provide the high voltage. So we use this rather new system from Cain. Also the Csec has a similar module, so you are not, you don't have to use this one. It's basically a cascaded high voltage power supply, which means that the potential of each channel is set with reference to the previous channel, which is a very natural way to power a gem stack, where also the potentials add up to about 3.6 kilovolts in our case. So this module can provide power to 2 gem stacks, so that are 16 electrodes. In our high voltage system, we also installed a shunt resistor that goes to gem 4 top, where we measure the highest currents. And the purpose of this I will explain on the last slide. Then we have decoupling resistors close to the detector, and then the usual loading resistors. And in addition, we have a PIsa system where we can send a pulse to gem 4 bottom that can then be read out through the pad plane for calibration purposes. Now to some detector physics. So this is an average signal from laser tracks. This is averaged over 1,000 events, which is nice because then all the noise disappears and you can appreciate nicely the features of the signal. The first thing you see is the common mode effect. So you have the large signal, and then on all the other pads, so this axis is different pads, you see a small signal of opposite polarity, and that is the well-known common mode effect. Usually you reduce this effect by adding an additional capacitor in the high voltage system. However, that can also carry some danger because this capacitor will store charge, and in case of a discharge, it could lead to damage to electronics channels or even to the gem itself. So we decided against that. And instead we have large FPGAs in the readout system, and they actually measure the baseline shift due to the common mode effect and remove it. You have maybe already seen that there's a funny tail in the signal, and that was a surprise to us. So basically we have an ion tail in our gem signals, and that through measurements and simulation we found that it has 2 sources. The first one is from ions that are created just below gem 4, so down here. They quickly disappear in the hole, but for a short while they can also induce a signal on the pad plane. And the second component is very specific to our high voltage settings. We have a rather large induction field, and there can be also a little bit of gain there. And due to this, we see this rather long tail. Also, this tail we cannot get rid of completely by changing the high voltage settings, so we will remove it in the CRU, in the large readout FPGA. that I will show also a bit later. This is our readout electronics. It's based on the Sampa chip, which is custom for ALICE. It has 32 channels with preamplifier, shaper, 10-bit ADC, and digital filters, which we don't use. We put 5 of these chips on one front-end card, and they continuously sample all the signals at 5 megahertz, and they continuously send all the data through optical links, which are the CERN GBT versatile link system. So all the ADC values are constantly being read out and sent off detector, and that creates a lot of data. The TPC produces 3.3 terabytes per second. And FPGA-based readout cards that I already mentioned, they receive then the data and do some first data reduction. On the right, you see the noise. We basically meet exactly the requirement of one ADC channel, which corresponds to 670 electrons at this capacitance. This is a schematic view of our data processing chain. So our TPC is installed in the Alice magnet. It is the main data source, so the other detectors add only 200 megabytes per second on top of what the TPC produces. We have 20,000 fibers connecting to a computing room. This is the first computing room, which contains 200 computers, which we call FLP. And each of these computers contain up to 3 of these FPGA-based readout cards, which remove the common mode effect, which also remove the ion tail and do some data compression. The continuous data stream is then sliced into so-called sub-time frames of 10 milliseconds length, and these are sent to a second computing cluster where we have GPUs. The GPUs do tracking, and we already find here the tracks. We remove all tracks that are not interesting, and we do some additional compression such that 100 gigabytes per second then end up at storage. This is a quick overview of our upgrade timeline. We started GEM production in 2016, readout chamber production in 2017, and the other steps I will show you on some other pictures. This picture shows you the outer readout chamber installation. So the chambers were inserted into the drift volume, then turned and then installed from the inside in order to maximize the active volume. After the installation of this chamber, we took a picture through the hole that is still left up here, and that looks like this. You basically look at a mirror. It is this shape here. This is the central drift electrode, and then you can see yourself, which is not visible, and you see all the gem stacks installed inside the TPC. After that, installation of readout electronics and services. That was still in 2020. And then the TPC was transported to the cavern for installation in the magnet. And we started connecting and commissioning at the end of 2020. One slide on calibration. So krypton calibration is a very common strategy for doing gain calibration of a TPC. You basically have radioactive isotopes in the gas, and then for each gem stack or even for each pad you can extract a spectrum, and from that you can determine the gain. And this plot shows you the gain distribution on a full sector, and you see some funny effects. There seems to be some sagging of the gem foils due to electrostatics. There might also be some wrinkles in the foil, and then this distribution in the outermost stack is actually, we know where it comes from. It comes from the hole size distribution of the gem foils that we got from the producer. Then the pilot beams in October 2021, we were exercising already our readout system. And this is an online plot that fell immediately out of the system after just a few minutes of data taking. So this shows you that the TPC works, and it also shows you that our online data processing chain that I explained a few minutes ago is also working nicely. one more slide on distortions. So without the gating grid, there's no way to have absolutely no ions in the drift volume. So there will always be some distortions left if you remove the gating grid. And at higher interaction rates, they can still be considerable. This plot shows you that you reach a few centimeters still, so they have to be corrected. We have already some experience because in the past we had some ion leakage with the gating grid. So what we do is we interpolate tracks from the TRD, which is outside of the TPC, and from the time of flight to the inner tracking system. And then with this we can measure the average distortions in the TPC, and we can correct for them. However, we know that in addition also fluctuations of the distortions play an important role if you want to get the perfect performance of the TPC. So we have to measure these, and this can be done in two ways, either based on the ADC values themselves. We sum them up and we calculate from the electron signals, we calculate the expected ion distribution in the TPC. And the second way is this resistor in the high voltage chain that I showed you 10 minutes ago. So there we can measure the analog currents in the high voltage system. So these calibrations are quite demanding, and they are the next big challenge for our project. So I have my summary here. The upgraded TPC has been installed, again in the magnet, already about a year. We have gained some first experience already even with colliding beams. Today we will probably have some colliding beams again at LHC injection energy. And the next challenge, as I mentioned to you, is the calibration of the data. And there's a link to our upgrade paper if you want to read more, and I thank you very much for your attention.
Thanks, Christian. So looking forward for collision. Yes. Are there any questions? Silvia.
Yes. First of all, thank you, because it has really been very clear and comprehensive. The point I am interested to understand is the following. You have underlined this need of calibration, which is very natural, of course. Now, which will be the interplay between the calibration and the online reconstruction that you have explained? Because there is a kind of time sequence, which is the strategy that you will adopt. Thank you.
Basically, we have a two-staged calibration strategy. The first one is the online one, which I explained in this slide. So basically, in this computing cluster, which is called CR0, we do a first calibration, which is based on the average space charge distortions. And we also extract calibration data, which you even see indicated here, that go then to storage. And then there's a second reconstruction and calibration step, which comes, which is not online with the data taking, which is asynchronous. And we go over the data again, and we correct also for the fluctuations of the distortions and try to reach the intrinsic performance of the TPC.
But this means that you preserve the whole set of data, at least up to this second calibration stage. Have I got it correctly?
We remove a few tracks, like for instance, in the TPC, very often you have some spirals and low energy stuff that is not important for the physics. And if you remove that, you gain a factor of 2, basically, already. So there's quite a bit of tracks removed that we know that they are not important. Then we also don't store the raw data, but we store clusters and tracks, which are smaller in size. And we do some additional compression in order to not use too much disk space. So there's a bit of data loss and compression involved.
Thank you.
My question concerns the switchover of MWPC to gem readout. Apart from the triggerless operation, are there other improvements which are mentioned? You can mention that you see, or is the performance otherwise, the E by the X and things like that, the same as before?
The aim was to have the same performance that we reached with the wire chambers, also with the gem system, and I think we have met this aim. Other advantages, well, they are the usual advantages of the gems over wire chambers, but on top of this, nothing special.
One last question.
Yeah, I think, thank you for the nice presentation. And I believe that compared with the old TPC, we will try to have a tracking up to 1.4, 1.5 in eta. No? This is also a new development.
This could be. I'm not fully aware of such thoughts.
Thanks. So I think we have to move on. So next speaker is Daniele Fasanella about longevity studies of the CMS muon system.
Okay, so I will talk about the longevity studies for the CMS muon system going towards high luminosity LAC. So CMS has an extensive muon spectrometer that was developed for LAC, and the original system already used a different gaseous detector technology, and it was covering a large pseudo-rapidity region. In the barrel region, we had drip tubes chambers. In the end cap region, we have cathode strips chambers, and then we have RPC in both regions. Thanks to this spectrometer, we had excellent performances in the run up to now for triggering, identification, and reconstruction of muons, which is one of the specialty of the CMS experiment. Now, an extensive upgrade is planned to cope with the new environment and challenges of high luminosity, where we will have peak luminosity much higher and a lot of pile-up events. And in particular, we will also integrate at least 10 times the LAC design value expected charge. So in order to strengthen our system, we are also adding additional detectors. So we already started in the last shutdown installing a gem detector in the forward region, and we will also install improved RPC. So in general, the test of the longevity of the full system is of critical importance and a critical part of our upgrade program. So the aging of the gaseous detector is mainly dominated by the background, which reach our muon spectrometer. So we can estimate what we will have at high luminosity LAC from in two ways. So first of all, we have started studying the background that we are already seeing. So we study currents and heat rates as a function of instantaneous luminosity. As you can see, we have essentially a linear behavior in all the detector, so we can extrapolate to the high luminosity LAC expected instantaneous luminosity. And also we are doing extensive studies with Fluke. In order to simplify, we have in general two main types of background that has been identified. Here we can see, for example, the segment in the DT chambers. We can have a direct background, which is coming from collision, which is essentially punched through. And then we have also neutron gas, which forms in the experimental cavern and give us a background coming from the top of the detector. The ideal place to test the longevity for all our detector is a facility which is a CERN, which is a gamma radiation facility. This is because it has a very strong gamma source, is a 12 terabecquerel cesium source, and also has a muon beam of 100 GeV. So we could both do accelerated aging and also test our chamber. This gives us a reasonable modeling for the condition of high luminosity LHC, and is particularly flexible because we can use the distance from the source and also regulable filters in order to fulfill the need of the different setups, so the different background environment that they will have in CMS during high luminosity. So let's start from the drift tubes. So the basic detector element is a drift cell, where the gas mixture is argon CO2, and then we have a gold plate steel wires that acts as a anode. So we started the aging studies in 2015, and what we observed was a fast degradation of the detector gain with integrated charge. So as you can see, what we were seeing is that the wires became coated because the avalanche condition around the wire was fixing impurities present in the gas, mainly coming from the outgassing of the detector itself. This was very, very fast, and in some sense was also suspiciously fast because up to now we have shown no signs of aging in our detector. So we have done now a second series of studies with virgin wires, and we have noticed now a slower aging. And also we noticed that in the analysis of the coating of the wire, we are no longer seeing carbon. So we are doing additional period and additional test to try to understand this behavior. In general, we have, in the meantime, studied the impact of this aging on the physics performance. So as you can see, this affects mainly the chamber which are in the inner region in the external wheels, but this impact is reduced at different levels. First of all, because we have 8 layers and only 3 are needed to build an offline segment. Then in phase 2, we will handle the TDC hits in the backend outside of the experimental cavern, and so we can also improve the algorithm in order to mitigate this effect. And also, as you can see, as you have seen, the CMS muon spectrometer is redundant, so we have also RPC and CSC in this region. So this loss, which is strong in this chamber, in the end is just marginal in the full reconstruction of CMS. At the same time, we are also putting mitigation strategy in order to reduce this aging. So to do that, we have reduced the wires voltages in the detector. So every 5 volt step is 30% less of integrated charge. And we are operating so the detector now with different voltages with respect to the region which are more exposed to background. Also, we have modified the gas system in order to move during operation to open loop in order to minimize the redistribution of free radicals, and also to reduce the effect of the neutron gas in the cavern. We have installed the shielding on the top of the detector, which is made of layers of borated polyethylene and lead. And the expected reduction is of the order of 30–40%. Moving to the CSC, so they are multi-wire proportional chamber, where we have argon, CO2, and CF4. We have also done here an accelerated with a factor 25 irradiation campaign at GIF++, both with a nominal gas mixture and with a reduced component of CF4. We have measured the charge for Unix X as a dose measure, and as you can see, we are now almost at 2 times high luminosity LHC, and we have seen no significant signs of chamber degradation. So we expect that we can operate CSC at high luminosity without many problems. The same is valid for RPC. Also here, so RPC are double gas chamber, where we have this gas mixture and is operated in avalanche mode. The RPC use the same gas mixture, but have a different geometry to cope with higher background region. So we have irradiated spare RPC chamber. We have collected also here almost 3 times high luminosity LAC, and we have seen stable performance, noise rate, and also a stable ohmic current, because one of the problems of RPC is the increase in the dark current. So also from the RPC, we don't expect any particular problem from the detector itself. The main problem for CSC and RPC is that they both use greenhouse gases. And as you probably know, the European Union has a specific regulation in order to phase down the production of this gas, so they will become also less available and more costly. So there is a CERN strategy in order to reduce the greenhouse emission, which is coordinated by CERN. So we have some short-term action. So the optimization of the current technology. For example, one of the main problems in the RPC were a leak in the barrel region. And so an extensive repair campaign has been done during LS2 in order to reduce this leak. And also, we are, in particular, the CERN EPDT gas group is involved in the development of recuperation system. So we have a CF4 plant for CSC, which is operational since 2012, and now has a recuperation efficiency of around 65%, and also is ongoing a recuperation system for the tetrafluorane for RPC, and we have already a prototype installed, and the system is running since 2020. But the long-standing strategy is looking for alternative gas. So having in detail a look to the Csec Gas Studies, so the main problem is CF4. So as we have seen before, we have done this irradiation test reducing the CF4 content. So here you can see a result with 5, 2, or no CF4 at all. So we have not seen a performance degradation, but we start to see a darkening of the wires, in particular when we are going without CO4. So moreover, there is an ongoing test for alternative gas mixture. For example, we have the CF3E and HFO, which have been investigated. And these studies imply both testing the performances with this new gas, and then also, in particular, the aging. So, in particular, the HFO is particularly interesting. There was no gain degradation with a sensible integrated charge, but we were start seeing an increase in the dark current. For RPC and IRPC, so this is a common problem because this kind of RPC detector are used in many experiments, and they all use similar gas mixtures, in particular with the tetrafluorane. And there have been found some good alternative with a mixture which uses the HFO and the CO2. But what is particularly difficult is that you have to fulfill all the requirements of detectors that are already installed. So they have a fixed layout, and also we need to study the long-term performance. So in particular, has been formed this collaboration, this EcoGas at GIF++, which is a joint effort with Atlas, CMS, LCB, and SHIP, and is also inside the IDA Innova task. So for example, it has been tested this 3 mixture with HFO. So the first mixture has been already discarded due to the increase in the dark current. And for the other 2 mixtures, they have been characterized with a test beam, and now the irradiation will start. Moving to GEM, so here we have a mixture which is again argon and CO2. And we have detector in a very different region. In particular, ME0 will have a huge integrated charge during the high luminosity condition. So we started the irradiation campaign at GIF. So with what we could integrate at GIF, we see that there was no gas gain loss. And we validated the GEM in this region with a good safety factor. But for ME0, something more is needed. In fact, it was used this facility with X-ray gun This can let us irradiate 8 times faster than at GIF++. We have facilities both in Aachen and in Seoul. And there was the first irradiation campaign that have validated ME0 up to 1.5 coulomb per centimeter square. And now we have an additional campaign ongoing. You see we are here, and we are going towards 3 times high luminosity LAC. So in summary, I've shown you the longevity studies for the differential detector for the CMS muon spectrometer. This is particularly important for the legacy detector that were developed thinking about the integrated charge of just LAC. And the result coming from GIF has helped also develop a mitigation strategy for the future operation. And also we have tested all the new detector, which will go also in a harsher region, and the final assessment of all the studies is expected in general within a year from now. In particular, is important this huge effort from CERN to reduce the use of greenhouse gases. So actions are already ongoing, so we are using a recuperation system and addressing the leak rate in the experiment. And at the same time, there is this large campaign of research and development. And then, if you are also curious about all the different gaseous detector SCMS, we have a large selection of posters that you can see also in the poster section. That's all.
Thank you, Daniela. Are there questions?
Thank you for this overview. In reducing the use of fluorocarbons, there is another parameter of gaseous detector that can be potentially affected, and it is that of the time response. One of the motivation for fluorocarbons is to have fast detector. Is this being studied, considered? Does it has consequences in the high luminosity era? Thank you.
So yes, it was studied by the C group, but yeah, for the but it has been seen as that is not a big issue. So the big issue is more on the aging side, but for time response and also what has been studied is also the resolution of the detector. It is not affected by the reducing the CO4 content.
Thanks. Are there other questions?
Beatrice, can I ask a point?
Yes.
Okay, thanks a lot for this presentation. I would like just to make one comment related to your agent studies. Concerning the DT, what you show the gain degradation, I mean with the argon CO2 gas mixture and showing the same analysis of the wire, you have a silicon peak, which is in principle not even larger than the carbon peak. And it is well known that in principle in the argon CO2 mixtures is very prone to silicon aging and not carbon aging. And this is also related to the use of CFO. CFO is a very good scavenger of the silicon. So this is the two elements which is actually just I wanted to point out, and maybe you would like to comment about this.
So yes, so we are aware that probably adding CO4 will solve all our aging issue, but as you have seen, is something that we are not even considering. And yes, we were expecting in the end the silicon, and we have seen that when we have only silicon, is still manageable. And we are trying just to understand this, the provenience of this carbon peak, that we can see that can be impurities that were not coming from the chambers, but are more coming from or externally of the system itself. So we are also doing studies directly at 0.5. We have also extracted the wires at 0.5, even if the charge integrated is still small. And we have not seen the same behavior, so it's under. For the silicon, yes, we think it's coming also mainly from the glues that has been used to assemble the detector at the time.
Thank you.
Thanks. Me too have one curiosity about the aging studies that I think are fundamental for the high luminosity LHC phase, but also for the future collider. My question is about the acceleration factor. How did you choose the acceleration factor, and it is the same for a different type of detector, or is different?
Every group has used a different acceleration factor. So this is linked to different reasons. So first of all, you have how much your detector can handle high rates and high dose. For example, if you consider the drip tubes, they are designed to be in a low background region, and so also the acceleration factor is reduced. Yes, it's also open in general the question how much this acceleration factor impact on what we are seeing. So we are also trying, for example, in the DT to use different acceleration factor and to see if this behavior is different, if there is also threshold level at some point. This will also explain why we are not seeing anything at 0.5 where the background is much lower and so on. So in general, the idea was to also combine the time available for the studies and so on. So it was decided sub-detector by sub-detector.
Thanks. Yes, it's not so easy to do aging tests.
No,
not at all.
In particular, in the gaseous detector, there is a lot of literature on this because it's complicated.
Any other question? Okay, so let's thank the speaker again. And we move on with Christoph. We speak about the development of segmented gem readout detector. You can go ahead.
Can you hear me?
Yes, very good.
Okay, I will show to you the development of a segmented gem readout detector. First of all, differently as the name suggests, it's based on a micromic gas detector. Here you can see the working principle. It's divided into two regions, a big drift region and another small amplification region. Both regions are separated by a micromesh here, which is lying on top of pillars which are giving the height of the amplification region. When an ionizing particle traverses the detector, it ionizes the gas along its path here, and the electrons will drift towards, due to a low electric field, to the amplification region, where we have a very high electric field which accelerates the electrons that much that they ionizes other atoms and so on, and we have an electron avalanche. And this electron avalanche is in the end collected on the anode, which is in my case a resistive layer. And from there it couples to readout strips, which are read out by readout electronics. Here you can see the used readout structure of the detector. On the top we have a diamond-like carbon resistive layer anode, and underneath we have two layers of readout strips, here in red and in green, which are perpendicular to each other, that we can reconstruct in the end a two-dimensional position. The detector is a floating mesh detector. That means that the pillar is just lying on top of the pillars and can be removed if wanted. To reconstruct a two-dimensional position works quite well when we have just one particle at the same time in the detector. If we have now, like in this case, multiple particles in each layer, we see an X layer and a Y layer, we can reconstruct two particles, but combining them to a two-dimensional position is not that doable, because we don't know whether the particle was here, 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 or here. So we need another information to reconstruct the two-dimensional position. One solution for that is to add a third layer of readout strips, as it is shown in here. We have X strips in black, Y strips in green, and V strips tilted by 45 degrees. Yeah, and by that we get an additional information, and it's now possible to reconstruct a unique position for each particle, because there are only two possibilities where all three readout strips intersect. And for identical particles at the same time with the same charge, you can reduce, as it's seen in here, the number of correct, increase the number of correct reconstructed particles by a factor of 2 to 4. In black, there is just for the X and Y strips, the fraction of correct reconstructed particle, and in green for all three layers. And a further improvement of the reduction of ambiguities is of course possible by using other informations like the signal pulse height or like the timing. But this simulation only focuses on identical particles at exactly the same time. So our idea is now to get the third coordinate at the position of the mesh, but it's not that easily doable to make readout strips on the mesh or segment the mesh into strips, because if you would segment the mesh into strips, we just have single wires. Therefore, the idea is to replace the mesh by a chamfoil, because a chamfoil is produced lithographically and can be segmented into, or one metal layer of the chamfoil can be segmented into strips which can be used for readout the signal. And this chamfoil is now directly mounted on top of the pillars instead of the mesh. By that we have now two amplification stages, one inside the chamfoil and one micromegas amplification stage, and therefore always two different amplification voltages we can play around with. Such a segmented chamfoil is shown in here. The top side here looks like a normal chamfoil. We have 70 micrometer holes every 140 micrometers. The only difference is that we have a more thick frame in here, because we only have a frame on the top side and not on the bottom side, because the chamfoil is directly pressed on top of the pillars, and therefore it would not be possible to have a frame there. The bottom side, just the copper on the side, is segmented into strips, as you can see in here. They have a periodicity of 484 micrometers, respectively 4 cham holes. And the strips are then guided here to some connectors where we can plug in our APV front-end electronics. And of that foil also an inverse layout exists when the top side is segmented and the bottom side is a normal cham foil. A prototype of this segmented cham readout detector was built, where we have the strips on the cham foil parallel to the bottom strips on the micromegas anode, just to test whether the reconstruction using that cham foil works. And yeah, this detector was then, so in the end we only get two different coordinates with that detector. This detector was then tested at a beam time at CERN. Two different setups were tested in a tracking telescope. We have 4 reference detectors, which gave us a precise reference track. And in the middle we investigated 2 segmented cham readout detectors, one with the segmentation on the bottom side of the chamfoil and one with the segmentation on the top side of the chamfoil. And the pulse height, efficiency, and also spatial resolution were investigated for different voltage combinations and different angles of inclination. Here you can see for all 3 readout strip layers in the detector the pulse height. You see the pulse height of the top anode strips, which are here, the black strips directly underneath the resistive layer. And the strips on the chamfoil, they show a similar pulse height, just a factor of 1.5 difference. But the pulse height of the bottom anode strips is quite off by a factor of 5 to 6 with respect to the top anode strips. And that's due to the design of the micromegas anode. But this is something which was improved by changing the design of the anode. And yeah, but these results are not shown in this talk. But in principle, the pulse height of both readout strip of the bottom readout strip layer and top readout strip layer will be the same in the future. Here you can see the efficiency for all 3 readout strip layers and for both setups with a segmentation on the bottom side and top side. And this reaches for both layers on the chamfoil and on the top readout strip layer on the anode, values above 90% for both setups. And as an efficient event, I consider an event when the hit is within plus minus 1 millimeter with respect to the reference track. The only difference between both setups is that here, if you look at the values on the x-axis for the amplification voltage, we have an offset of around 20 volts, which is due to mounting of the detector. To determine the spatial resolution of the detector, we have a look at the residual, which is the difference between the reference track and the measured position in the investigated detectors. This is then filled in a histogram, like at the bottom here, for multiple events, and fitted with a double Gaussian function. And the reason for the double Gaussian function is that the tails function at the bottom considers multiple scattering or delta electrons. To obtain a value for the resolution, the track accuracy is subtracted quadratically from each sigma, and then each sigma is weighted by the integral of its Gaussian function, and in the end we get a weighted sigma, which is a measure for the resolution of the detector. This is now shown in here. First of all, in the columns we have different CHEM voltages for 300 volts here, 200 volts and 100 volts, and on the x-axis different amplification voltage in the micromegas region. And you can see in here the resolution of the top real strips on the anode and the CHEM strips are quite similar, and they reach values up to approximately 80 micrometers at a voltage combination of 200 volts in the CHEM foil and 440 volts in the micromegas region. And due to the lower pulse height of the bottom real strips on the anode, this is not at the working point, and we only reach 100 micrometers. But this is something which will be fixed. Yeah, and if you look closer, you see a small discrepancy between the signal, between the resolution on the CHEM strips and on the anode strips, and this is because we are using a resistive layer anode, and there the charges will spread in all directions, and this electron spread is resolved, and this influences the resolution of the detector. But this is something which can be corrected for, and then we reach the same resolution for both layers. The previous shown results were just for perpendicular tracks, where we used the charge-weighted mean to determine the position. But it's also possible with the detector using the so-called micro-TSBC method to use the timing of each signal to reconstruct the incoming track. For example, an electron which is created closer to the CHEM foil has a shorter drift time into the amplification region as an electron created closer to the cathode. And by that one can reconstruct, as shown here, the track of the incoming particle, a position which is corresponding to the middle of the track, and furthermore, the angle of inclination. And for multiple events, this angle of inclination is shown in this picture here. You can clearly reconstruct an angle of inclination of 20 degrees. And to obtain an angular resolution, this distribution is fitted with two Gaussian functions, one closer to angles 0 and one closer to larger angles. And the reconstructed angle you can see in here, 20 degrees can nicely be reconstructed, as well as 26 degrees. And this blue shade behind here is the angular resolution, which is also shown in these pictures here, one for angles closer to 0 and one for angles closer to larger angles. And yeah, the angular resolution is at 20 degrees, approximately 2 degrees, and at 26 degrees, approximately 3 degrees. And the resolution of the reconstructed position using this method is shown here for different CHEM voltages again, for 20 degrees. And with the readout strips on the CHEM foil, this method is working quite well. We reach values of around 200 micrometers, or better than 200 micrometers, with that micro-TPC method, and compared to the charge-weighted mean method, this is much better, because now we just reached 350 micrometers due to the inhomogeneous ionization along the particle track in the drift region. And for 26 degrees, we reach values of around slightly better than 200 micrometers, which is far better as the corresponding charge-weighted mean position. One needs to consider for that we use APB readout electronics, and the clock of the APB is sampling in 25 nanoseconds, and this is not correlated to the trigger signal. And therefore, we have a jitter of maximum 25 nanoseconds, which yields to a maximum uncertainty of around 200 micrometers. This is something which can be measured and corrected for later on. And yeah, to finish up this talk, I would like to show you the an iron 55 spectrum, iron 55 pulsate spectrum. It can be seen in here as a measure for the energy resolution of the detector. You can clearly reconstruct the gamma peak and also the argon escape peak, and both peaks should be a factor of around 2 different. And this factor of 2 is also reconstructed with the top anode strips and CHEM strips approximately for different voltage combinations in the CHEM voltage and for different amplification voltages. And there's another measure for the energy resolution of the detector. One can take the width of the photon peak and divide it by the position and get a factor of around 22% for the energy resolution. As a summary, I can say I have a well-working segmented CHEM readout detector where I can obtain one coordinate with readout strips on the CHEM foil and a second coordinate with readout strips on the anode, on the micromegas anode. And it also is with a new anode layout possible to obtain also a third coordinate, the B coordinate, and have a well-working XYB detector. The resolution in the both investigated coordinates with the CHEM foil and with the top readout strips is best 75 micrometers for perpendicular tracks and around 200 micrometers for inclined tracks. Yeah, and as a next step, I will for sure build the XYB detector now, since I know that it will work. Thank you.
Thanks a lot, Christoph. Are there any questions?
Yes?
Ah.
Standard GEM detectors are also sectored for different reasons, though. It has to do with the energy on the discharge. And there are clear measurements that show that locally in the region of the separation, there is a small loss of efficiency and accuracy. Is that, well, this I haven't seen in your data except for the number there, 90% efficiency for trucks, which seems could be the reason, could be due to this.
Actually, I didn't have a look at the gaps between the strips, but or not in detail, but on the first side, at least the beam profile was nicely reconstructed, and I didn't see any effects at the border of the readout strips. Maybe that's because I also have the micromegas amplification region, which kind of compensates that factor.
Maybe there's a complicated explanation, but my explanation is that simply the regions between metals do not transmit the electron, or partly transmit the electrons in the GEM amplifier.
Maybe if you look closer here, at around each hole there's, it can't be seen very clear, but there's all the holes are surrounded by copper, and therefore
no, that's not true. There are some measurements, you certainly know them if you are in contact with Leszek Kropalewski and his group. With optical detection of the image of the radiation, which makes a very nice image of what happens, it's clear that the holes that are not covered by metal do not amplify, so
no, but
do not transmit, or transmit partially only.
But if you look close, that are not straight lines between the holes. This is like snake lines, so that all the holes are.
Well, this doesn't matter. The problem has been solved by putting a DLC layer under the metal. Yeah. And then what is here is Kapton, uncovered Kapton, is in fact slightly conductive and therefore keeps the field.
Yeah, maybe.
But it's a complicated technology.
Thanks. There was one question over there.
Thank you for the talk. Do Do you plan to do any measurement with magnetic field? Because the orientation of the planes, the readout planes, they typically depend on the magnetic field condition.
Up to now, it's not planned to make any measurements with magnetic field. One main reason for that is that we want to resolve Cherenkov cones with it, which have multiple signals at the exact same time. So for that, we don't need magnetic fields.
But if you have any magnetic field, your Gauss teeth reconstruction will be strongly affected.
Yes, I think so.
Yes. Do you have an application already in mind, an experiment?
At our chair, someone else is building a kind of Cherenkov ring imaging detector using a gaseous detector, and for that we need to resolve the position of all the photons in a better way as it can be done with pixelation, and therefore we need this reconstruction of multiple.
There you have a strong competition of the silicon PMs.
But we want to make that large scale, so yeah.
Okay.
Thank you. Any other question? So then we move on. Let's thank the speaker again. Okay, next speaker is Aude. Did I pronounce correctly? Yes. About the ion backflow. That is a very important topic. We also see that at the beginning with the Alice TPC.
Thank you. Hello, so I want to start off by thanking the organizers for this very nice workshop and this opportunity to present the work conducted at CEA. So the R&D work performed at CEA was to try to optimize and perform like generic readouts, generic research and development of micro pattern gaseous detectors in order to apply them to TPCs as readout detectors. So this is a sketch of the Phoenix TPC. The Alice TPC is very similar, where you have the central cathode, and then at both end plates where you have the anodes, the readout detectors. These can be, for example, multi-wire proportional chambers, but now they also use micromegas detectors and gems. So for example, in Alice and Phoenix, they use quadruple gems. So micromegas detectors have been nicely introduced in the previous talk by Christoph, so I'm not going to introduce them again. And the gems also have been introduced. So you have the insulating foil, which is pierced by different holes, and which are covered on both sides by a couple layers. By applying different electric fields, there is a high field region within the holes where an amplification occurs. And the kind of issue with both technologies is that when you have this amplification that occurs, the electrons drift downwards in this case, but the ions can go upwards. Most of them will be stopped at the micromesh, or here they will be stuck because of the drift field at the gem. But some of them might still drift upwards and reach the drift region. The drift region, which here then would be the TPC. So this might induce local distortions of the electric field in the drift region, which could then deviate particle trajectories, and hence a degradation of the spatial resolution of the readout detectors somehow. So the goal of this R&D was to design and test new combinations using micromegas and gem detectors to suppress completely this ion backflow. So, there are several solutions that exist. So as I said, in Alice and Phoenix, they use quadruple gem detectors as readout detectors. There have been studies indicating that twice the better ion backflow could be obtained by micromegas detectors plus 2 GEMs. And now we want to offer an alternative that also uses GEM and micromegas, where we would have a micromegas 128 micrometers above the anodes and the pads, then a few millimeters above a GEM, and with only a few hundreds of micrometers gap above an amplification mesh that would inherently suppress the ion backflow. So we performed the tests with the standard requirements for TPC readout detectors, such as what was required in ALICE and Meg experiments, which used the drift field of 400 volts per centimeter. They're required to have a total gain the readout detectors of the order of 2,000, and they had to keep an ion backflow lower than 0.3% in order to have a continuous readout of the TPC. So first, we started with simulations using the Garfield++ software. So the first 3D electric field maps were simulated in the software console. Here, in this simple example, this is just a micromegas mesh represented, where we have a ionization that first occurred at one of these points. Then, so the electron is represented with the yellow line. It drifts until this level where there is the mesh. And here the amplification occurs. So the ion tracks are represented in gray. Most of them seem to be stopped for this Z corresponding to where the micromesh was placed. But some of them here, for example, one of them here was able to escape. So in this simulation, the ion backflow is simply defined as the number of ions that escaped divided by the number of ions created in the avalanche. And the gain is defined by the number of ions in the avalanche. So now the model is becoming more complicated. This is a whole transverse view of the detector simulated that we're going to test, where we have the micromesh here at 128 micrometers above the pads. Then the gem and the mesh, in this example, it's 128 micrometers just above. There are several geometric parameters that we tested and that were varied during the simulation. So for example, the gap between the gem and the micromesh, that was varied up to 600 micrometers. The pitch of the mesh and the wire radius. So what is very complicated here is that you can see that we have two amplification stages that are very superposed. So two regions of high electric field. So this makes it the complicated thing. So this is an example of results obtained with the simulation where we had very promising results. So this shows on the left the electric field configurations of the detector with the altitude or the Z position of each electrode. This diagram here shows, depending on where the electron started, so depending on where the avalanche was created, where the electrons were stopped. So we can see that the electrons that reached the drift electrode only were created only below the mesh top, and the mesh top here is very effective at stopping all other amplification electrons from the stages below. The simulation was performed with a iron source. So you can see here the spectrum simulated with a gain of 2,000. And finally, the ion backflow here is represented for each event, fitted with the Gaussian function. And here it seems to say that the ion backflow could be as low as 0.1%. So the next step now was to build and test prototypes. We had two detectors to test with different geometric parameters. So the gas mixture that we used was always argon and isobutane. We used an iron source to create our events that generates photons at 5.9 keV. The mesh, the bottom mesh here was always the same. So it has a 45 micrometers hole size and 18 micrometers in diameter. The gems were created at CERN. They are 60 micrometers thick with an outer diameter of 70 micrometers and an inner diameter of 50 micrometers. The first detector tested had an amplification gap here of more than 6,100 micrometers. And the mesh top used was the same as the one below. And the second detector had a smaller gap and a larger pitch and a larger diameter. So here the spectrum are obtained using the ORTEC preamplifier and the multi-channel analyzer module. The ion backflow is measured because obviously we cannot just count the ions, so using the currents on the mesh and the currents on the drift. So what we wanted to see was the displacement of currents when using the iron source. So this was done using the pico ammeter, and the ion backflow is given here, where we can see just the displacement of the currents on the drift divided by the displacement of currents on the mesh that will represent the gain. And we have to subtract by 1 over gain to account for primary ionizations of photon, because of course when the photon comes in and ionizes, the ions also drift, but these are not really these are not ion backflow. So now we are going to slowly go into all the different amplification stages to understand how they work. So first is the simplest configuration. This is just basic micromegas configuration, where we want to see the behavior of the micromesh here. So the electric field here was fixed. The drift field, the drift electrode for this measurement was placed just above the micromesh, and then the gem and micromesh were used as screen electrodes to make sure that we could apply an electric field in the other direction and prevent ionizations occurring above the drift electrode. So we increased the field in the amplification region to get the gain and the ion backflow as a function of this field. Second is the second parameter to vary is the field here in the drift region. So the gain of the micromesh is fixed, and now we're looking at the transparency of the mesh, so this capacity to extract the electrons coming from above. The ion backflow here seems to scale linearly with the field here in this transfer region. And so now is going to be the more complicated step, where we want to see what happens for events that take place in between the gem and the top micromesh. So there are 3 steps to understand the behavior of the mesh. First is going to be the extraction of the electrons from the mesh, which is also combined with the gain of the gem. So this is a quite complicated measurement to make, because this region here is only 600 micrometers thick, compared to this region, which is a few millimeters thick. So most of events would come from there. And you can see here the gain spectrum. So the gain of the gem is represented by the brown curve here. This peak here is the escape peak after the events past the gems. And then, so similarly, in order to quantify the extraction of electrons from the gem, we had to increase the electric field transfer here. So by looking at both curves, we were able to extract, so here, the gain, which is convoluted with the extraction of electrons. In order to see the effect of the gem of the ion backflow, which is represented as the black curve here, it is compared with the what happened without the gem. So we can see that from a certain transfer field, the gem becomes efficient at stopping ions. And finally, so using these previous curves, we're able to deconvolute the extraction of electron and the gain of the gem itself, which is represented so here. And finally, last step to characterize the gem was to look at its transparency. So we're still looking at these events, and the variable that we have now is to increase the field below the mesh top here. And we can see that, well, the transparency decreases quite fast with the electric field. The ion backflow itself seems to increase and then decrease and so reach a plateau. And this was considered to be true for both prototypes since they used the same gem and bottom micromesh. Now, using all these different curves, we're able to fix some parameters for the electric field configuration. So typically, we wanted to optimize the transparency of the gem and the ion backflow. So the transparency is very important because it has an impact on the energy resolution. And we wanted to, so similarly, the electron extraction also impacts the energy resolution and had to be increased. And this allowed to fix some of the electric field parameters. Now, looking at the first prototype with the large gap between the gem and the micromesh, the total gain was, well, is showed here by increasing this field here. What is interesting is that the transparency of the mesh itself increases, but the transparency of the gem decreases. So there is a plateau here until it starts to really increase, because that's the point where there is amplification occurring below this top micromesh. So here's the mesh top transparency obtained by deconvoluting with the extraction of the gem. So the ion backflow measurements are represented here. We were able to reach levels of lower than 0.3%. And this is an example of measurements for a gain of the order of 3%, where we can see that the ion backflow reaches value of 0.2%, which is quite good. Only the resolution is of 26%. And the second detector, well, had a very different behavior, because as opposed to the first one, which didn't really have amplification in between the micromesh and the gem, this one really does have an amplification. Also, so because the geometric parameters are different in this mesh, it's a lot more open. So the ion backflow here are twice as big as the values for the bottom micromesh, which is more closed. And finally, so here is the total gain of both prototypes represented, where we can clearly see that here the flat black curve shows again that there is not amplification between the below the top micromesh, as opposed to the other detector. The ion backflow seemed to be better in the first prototype, so reaching values of 0.3% and below. The second detector was also able to reach lower values, but because it has this gain very high in the detector, it has, well, lower performances in terms of ion backflow. And finally, this is the plot of ion backflow as a function of resolution on the right and of the gain on the left. So we didn't seem to have such a trend as shown by the first talk by Christian Lippmann, where with quadruple gems, they clearly had a structure going this way. But still, so we don't reach the level of very low resolution, but we are able to reach values of 0.3% of ion backflow. So this is a picture of the gem over the, of the micromesh over the gem. We were able to operate and test this new structure that had never been tested before, and to operate it at quite low gains, so of the order of 2,000 to 4,000, while keeping a very low ion backflow. And we have just submitted an article about this new prototype. So yes, so we expect the test to continue with new results. Thank you for your attention.
Thanks a lot. Very impressive work. Are there questions? Fabio?
With so many electrodes and voltages, you really have a lot of fun finding the optimum for your measurements. So congratulations for the patience. But if you show your first slide, I have another comment, more serious. In fact, any of your slides. Yeah, well, the general structure, not the first, the one with the structure, the combined structure.
Ah.
The third, maybe, I don't
This
know.
one.
No, the schematic, here, okay. The inevitable ion feedback is due to the first amplification region.
Yes.
It's just a ratio of the fields, right?
Yes.
Drift over a multiplication field.
Yes.
So I don't know which field you use, but if you want to reduce that, you have to have a rather high amplification, first amplification field. This means that the gem electrode gets most of the electron produced there because it collects that at the higher field. So at the end, I think the balance is negative. My question is, are you sure that by removing the first amplification mesh, you're not getting better results? And this is, by the way, the solution adopted by the Compass Rich 2 detector. That is a hybrid structure with a micromega as last multiplier and gems above. I don't know if Sylvie is around to comment on the value of the ion backflow that they get.
Yes, over there, Silvia.
Thank you. So, about what we did in Compass, we have used above the micromesh structure 2 layers of thick gem in that case. And our ion backflow is near a little bit below 3%. But I have another comment. There is another scheme that was presented in the past, and I even recall a talk at this conference, previous issue, to attack the problem with double mesh micromegas. And this is done in particular by a group in China in USTC, and they were reporting extremely low ion backflow, better than 10 to the minus 4, which is really great. So before making the scheme so complex, have you tried this double micromesh approach? Has it given any good
Yes.
indication to you?
We have tried double micromesh structures that were built at CE, and we also tested actually the detector from the USDC group. Well, what they claim actually is to have an ion backflow as low as 10 to the power of minus 4, but for gains reaching 20,000. So in the end, for gains of 2,000, the ion backflow was not as good. And in our measurements with the double micromesh structure, we had a very terrible energy resolution when using double mesh. So it was very hard to even have a precise measurement of the gain.
Thanks. Other questions? Please.
Maybe just a comment. So when we did R&D for the LSTPC upgrade, we also looked at the combination of micromegas and gem foils. So we just had the lower micromegas mesh on top of our pad plane and then gems on top of that. And that was also giving quite nice results. However, we abandoned that then because we rediscovered the usual discharge behavior. So we were afraid that our electronics would not survive this combination. So that is a potential risk that you have not really discussed here.
Yes.
Thanks. I have a very naive question
Yes.
about the gas mixture. You tried argon, isobutane, 95.5. Did you try also other gas mixtures?
No, we didn't try the cosmics. Just, you mean measurements of the cosmics in the detector?
Using other gas mixture or changing the concentration of isobutane, for example.
So no, we didn't try this. No.
Other questions? Okay. Then let's thank the speaker again. Okay, so last talk before the coffee break is about the poster review. I can use this one, no problem. Okay, so as we said at the beginning, this poster review is really crowded. We have 40 posters in this section, ranging from existing system, upgrade for high luminosity LAC, and pure R&D project. With Maxime, we decided to divide, basically to show to you by detector type. We have 8 posters about wire chambers, 3 about TPC. As usual, a big chapter about micropattern gaseous detector, RPC, and some posters related to eco-friendly gas mixture and gas properties. A thing that we would like to underline is that most of these posters are actually in line with the ECFA roadmap. And we would like just to underline that some keywords that you will find also in the summary of the poster. So that are in the ECFA roadmap. So time and spatial resolution, high sensitivity in low and high pressure TPC. Very important, we have seen also before, the long-term stability and aging test, the use of eco-friendly gas mixture for a future detector, and to achieve good tracking in gaseous detector with the dx over the d over the x and the n over the x. Another important point is that some of these topics are really very important for the future, as we have seen from Jan Shipsy Monday talk, where in red you have things that must happen, otherwise the physics goal of the future cannot be achieved. So let's start with the drift chambers. We see that main chapter is about Atlas and CMS upgrade, but as well as some work for the Meg and the IDEA detector. So we have 2 posters for the Atlas new small muon drift tube. The first one is about construction and testings. So they will build 46,000 new small muon drift tubes, so very impressive number. And the poster is about testing. A second poster is about the use of a new amplifier shaper discriminator that is necessary to cope with the high background radiation rate that there will be in the high luminosity phase. Also, CMS is doing an upgrade for the drift tube with an upgrade of electronics. A slice test has been installed in LS2 and is properly working. Moving to the Meg detector, here we have 2 nice posters. The first one is about detector calibration, especially using a 70 MeV lithium line. Some simulations are ongoing about that. And the second poster reminds to us the importance of the gas mixture composition for the gaseous detector. And here there is explained a gas monitoring tool to monitor the gas mixture. This poster is about the drift chamber of the CMD3 detector. Here the main topic is to have high transparency in terms of multiple scattering contribution to the momentum measurement, and by reducing the amount of material. And the second important topic is on the cluster counting technique. The cluster counting technique is also the main topic of the poster for the IDEA drift chamber. In this case, I did both simulation and beam test in order to understand the cluster counting technique. In particular, in this plot, we can see that they managed to have a resolution to time better with the dn over dx instead of the d over dx. The beam test results confirmed what has been seen in simulation, and they were useful also to define a set of parameters for the optimization of the cluster counting efficiency. And this is online also with the ECFA roadmap. If we move to the TPC, we already see a nice talk about Christian, and here is TPC for the future. So here is this poster is about the development of TPC for the ILD. Not only for the ILD, this is also studies are ongoing for the CPC and FCCE. In particular, in the poster, we also see that the readouts is being investigated with GEM, micromegas, or GEM plus micromegas stack and grid pixies. Also there, important is the double track resolution and the energy resolution. This poster is telling us that TPC can also have other uses. In this case, they're used in the spectrometer of this collaboration. So we have multi-wire proportional chamber and TPC with a readout made of 3 gem foils. It's very nice also that the scalable readout system of RD51 is used with the SAMPA. And this last poster about TPC is about actually a fast simulation. And this is reminding to us that simulation are also very important for the understanding of the gaseous detector. And also this is online with the ECFA roadmap, where specific software for instrumentation are needed for the future. If we move to the micropattern gaseous detector, we have decided to divide by type. So we have several posters about gem detector, micromegas, or micro-rewell. Starting from the gem and starting from the Csec experiment, this is a nice poster that is reminding to us that the gem was successfully installed in CMS in LS2, and this is about operation, especially to define a safe operation procedure during the CMS magnet ramp-up. Looking to the future for the gem in CMS, as we have seen also before in the talk of Daniela, there will be the installation of the GA21 and ME0 chamber in the future. So the first poster is about some test beam in order to evaluate the efficiency noise level, and the space resolution of the triple gem for the GA21. The second poster is about ME0 and especially the high luminosity upgrade, where we will have to cope with 5 particle rate. And here a solution proposed is to use a new type of segmentation, the azimuthal one. Stay on the subject of high particle rate. Here is a nice poster about an R&D project called Room Resistive High Granularity Micromegas, with the goal to arrive to reach an efficiency work at a particle rate up to several tens of megahertz per centimeter square. In particular, in this poster, we can see that several small pad micromegas prototype were tested with different layout on the spark protection resistive scheme, reaching very good rate capability. Coming back to GEM, this is a nice poster that reminds to us the flexibilities of this micropattern gaseous detector. In particular, in this case, we have the triple gem detector in a cylindrical shape for the inner tracker of this experiment. Stay on the gem, studies are also ongoing for looking at position resolution. Also in this case, there is the use of this scalable readout system that is really flexible for different type of studies. And another poster about the simulation to study the effects on the space charge phenomena in a gem detector. Moving to the micromegas, this poster reminds to us that with our gases, we can work at different pressure, low or high pressure, and the detector performance can change. In this case, these are related to the micromegas performance with a low pressure gas mixture. This poster reminds us also how micromegas can be used for different purposes. In the first one is about a pre-shower detector that is based on micromegas intervened with tungsten absorber. We have seen also in the calorimeter section actually how micropattern gaseous detector can be used in calorimetry, so a very nice application. And the second poster is an upgrade on the Amber experiment, so NA66, where micromegas with different geometrical properties are under studies in order to replace some detector that are doing aging. Micropattern gaseous detector will be also used for the Athena experiment, so for the electron-ion collider. In this case, it's very nice because 3 different technology will be employed. We will have triple gem detector, micromegas, and a large area surface of micro-rewell. So this is in track with the ECFA program. This poster is about 2D intervaled readouts for micropattern gaseous detector. And the poster is very nice that we can see that this can be applied for a different type of microparticle detectors and is working very well with a better spatial resolution with respect to the standard straight strip array. And this type of readouts is really suitable for the EIC application. Thinking about again the future, this is a poster where the PICOSEC technology is proposed for the muon detector of the muon collider, where the main challenges arise from the short muon lifetime and the harsh beam induced background. Last but not the least, here is a poster about the possibility of using micro-well technology for the pre-shower muon detector of the IDEA detector. In this particular poster, the idea is to do study on resistivity effects in order to evaluate the charge inspection effect. Stay on the concept of resistivity, that is a key element nowadays for micropattern gaseous detector, but also for RPC. We move to the RPC. So, thinking about resistivity, this poster is very nice. It's about surface RPC, so an RPC that is based on resistivity on the micropattern gaseous detector technology. This is a good combination between two different technologies that can combine. In this case especially, we make use of the diamond-like carbon developed for the Micromega Synergy 51 for the RPC. Where the resistivity is a key element for the rate capability. And speaking about rate capability, the idea is also to have a high rate capability with a high density current evaluation scheme. Stay on the improving rate capability for RPC. The idea in this poster is basically to decrease the resistivity of the RPC by increasing the operational temperature up to 40 degrees. And we see in this plot that they were able to reach a very good efficiency with high particle rates. Speaking about material for the RPC, the first poster here is about the use of 3D printing for building the detector and to use a new electrode material graphene doped. And the second poster is about the critical point of using linseed oil for backlight RPC. In this case, they are putting the linseed oil coating before the closing of the gap. About CMS experiment, we also seen before from Daniele's talk. CMS is going also to upgrade the RPC system with new improved RPC, where the gas gap, instead of being of 2 millimeter, is 1.4 millimeter. And in order to cope with the high particle rate and the pile-up environment of the high luminosity LAC, they also developed a new front-end board. RPC are not only used for high-energy particle physics. This is a nice example of a project in Italy where they're using multi-gap RPC telescope. So the project is called EEE. And this poster is about a new waveboard to prepare a streaming and synchronized GPS acquisition system. Another important topic of the poster session is about gas properties and eco-friendly gas mixture. As we have seen, so this is in the ECFA program. Stay on the EEE project. In this case, they have 60 detectors made of 3 multi-gap RPC that are operated with a gas mixture containing basically almost full R134A. In this poster, they tested different gas mixture. In particular, they have encouraging results with a gas mixture that contain helium and HFO. Concerning eco-friendly gas mixture, this is about testing RPC for the LEC experiment, where the difficulties stay on the fact that the detector themselves, electronic, front-end board, cannot be changed. So finding a good gas mixture is really different, especially also because we have to think of the radiation level that we have. In this poster, some alternatives to both R134A and SF6 are proposed, as well as the studies of impurity that arise from this freon molecule. Another way to reduce the consumption of gases, of greenhouse gases, is maybe to try to reduce the gas flow. This poster is about that. So it's looking at detector performance with a very, very low, ultra low gas flow. We also have to remember that it's not only a matter of studying new gases, it's also a matter of understanding the property of the gases that we are using. And this poster is about that. So it's a very nice new experimental setup that is measuring the electron transfer diffusion. Here you have a schematic view with a xenon lamp, a cathode, cesium ions photocathode, and then we have a drift path, and then amplification with gem foil. Results obtained are in agreement with existing data. On the same line, this poster is presenting an experimental setup for the measurement of mobility of positive and negative ions with the goal of further understanding the transport properties of ion in gases. As a last, an application of what you have just seen, this is to evaluate the electroluminescence yield of methane and isobutane in this special gas mixture made of helium and CF4. Very good results have been found with the use of 7% of methane to increase the WIMP sensitivity of dark matter detector. Last but not the least, we have seen before that we have basically new detectors that have to be built, and this new detector will have to face a radiation level that we have never seen before. So very important is to look all the time at the construction of the detector and possible aging issue. The first poster here is about the Meg drift chamber. In this case, it's about the problem of humidity in the chamber that could cause the corrosion of the wire, as you can see here. And so it reminds us that it's very important to have a controlled condition in our detector. This also is about, again, humidity. In this case, is gem performance in presence of water, so what's going to happen. And the problem of a short pathing gem, that this is an idea to use ultrasonic bath to remove the short path in the gem detector. And last but not the least, speaking again about aging test, this is a nice poster about long-term neutron radiation studies for a micromegas detector. They managed to accumulate a charge equivalent to 10 years of high luminosity LHC in Atlas, and they tested two gas mixtures, argon CO2 and argon CO2 isobutane, that is the gas mixture that will be used for the micromegas of Atlas. Very good results were obtained. We basically, after these 10 years of accumulated charge, there was no change in the pulsate for the detector tested. Coming to the conclusion, so a lot of posters, 40 posters that I invite you now to go and see during the coffee break. These show us that there is basically a large interest in the community in this field, and that several technologies are under study or under improvement. By looking at system type, we have upgrading of existing system or new systems that are in final phase of studies or under construction. And gaseous detectors are fundamental not only for the operation of the LHC, but also for the future collider. All what we have seen, or most of the things that we have seen, are in line with the ECFA roadmap, where I remind to you the key point, the rate capability of this detector, this is fundamental, spatial and time resolution, use of eco-friendly gas mixture, and the aging effects that we will have to face with the increase of the radiation. Let me also make a final advertisement. The idea with Maxime is to have then actually a gas detector aging workshop for next year or in 2024. Remember that the last workshop were in 96 and 2001, so it's time really to go ahead and look for this aging test. And other two workshops about gaseous detector that will be this year is the resistive plate chamber workshop in September at CERN. And in December, there will be the micropattern gaseous detector workshop. Thank you. So the poster, as usual, is in the next room. I invite you to go during the coffee break, and we will meet again. in 20 minutes. Thanks a lot. Let's wait 1 more minute. Okay, let's start. Next speaker is Marco Chiappini, that will speak about the cylindrical drift chamber of the Meg experiment. Thanks, Marco.
Good morning, I hope you can hear me. First of all, thanks to the organizer committee for the opportunity of being here. I will try in this short time to give you an idea of the work, efforts and challenges behind this detector. Along the presentation, when you see an underlined word, you can find an hyperlink in the PDF of the presentation to a paper for where you can find more details about that topic. This is the outline of my presentation. After a brief introduction, I will enter the main topic of this talk, and I will go through the bullets in a sort of a chronological way. So from the design and construction to the commissioning at Purification Institute, then the problems encountered along the path and how to solve them, and eventually the preliminary performance with the first physics data acquired during the 2021 data taking run. Just an introduction to the Meg experiment. The Meg is hosted at the Purification Institute, where the most intense continuous muon beam in the world is stopped in a slanted thin target. And so the muon decay follow two-body kinematics. You can find here the variables which fully characterize the event. Talking about the background, so we have the radiative muon decay and the accidental background where a photon and a positron coming from two separated events mimic the signal event. In high rate environment, which is the Meg case, the dominant background is the accidental one by one order of magnitude. The Meg experiment represents the state of the art in the search for mu gamma decay, and with the first phase, this experiment set the world best upper limit on this process, and an upgrade of this experiment was approved, and the goal of MET2 is to improve the differentiation by almost one order of magnitude in 3 years of data taking. Here you can find here on the right the final goal. How? By increasing the muon stomping rate and improving the detector figures of merit, like the efficiencies and resolutions. You can find here a sketch of the Meg2 apparatus, and outside the Cobra superconducting magnet, we have the 900 liquid xenon detector, 900 liters liquid xenon detector. We measure the energy and timing of the photon, and then we have the spectrometer to measure the positron energy vector and timing with the pixelated timing counter. Then moving on the drift chamber, I will go through these bullets, and meanwhile you can see on the left a table which summarizes the performance on this detector based on the most updated reconstruction algorithm with full Monte Carlo simulations, and we have still margin of improvements for these numbers. And so this detector is a low mass sink volume detector with high granularity, filled with a 9010 helium isobutane gas mixture, plus additives to improve the operational stability. We have 9 layers for a total of almost 12,000 wires. We have a small drift cell, a few millimeter wide, to keep under control the occupancy, especially at the center of this detector where the target is. And this detector has an high transparency. Here you can see a comparison between the MEG2 drift chamber and the MEG drift chamber system to minimize the multiple column scattering and photon background reduction. The single liter solution was measured on prototypes to be below 120 microns. And due to the extremely high wire density, this drift chamber is the first chamber ever designed and built in a modular way. And now I go into the details. So the end plates are the core of the mechanical structure of the chamber. It has the shapes of a ship's wheel. And we have 12 30-degree sectors, and we have wires strung in stereo wire geometry for the longitudinal heat localization. Talking about the wiring are not strung directly on the chamber, but they are wound around this wiring drum and then soldered on the soldering pad of these peculiar wire PCBs. And then we cut the excess of the wire between the PCBs, and we have the wire tray to be mounted on the mechanical structure. You can see on the top right picture a sketch of one 30-degree sector where the dimension of the cell are highlighted. And as you can imagine, due to the wire geometry, we have a set dimension varying with the radius and also with Z. We have different types of wire. So we have the sense wire, which is the 20 micron tungsten wire with gold plating. Then we have 40 and 50 micron silver-plated aluminum wires with a 40 micron ground mesh between layers. And then we have guard wires to shape the field at the border of the sensitive region, and to equalize the gain in the innermost and outermost layer. And the field to sense wire ratio is 5:1. Here you can see the final stack of wire PCBs in one sector. We use peak spacers to have the correct radial dimension of the drift cells. You can see the PCBs with the signal tails and the ground tails at the center. And through a survey campaign with the coordinate measuring machine, we were able to keep under control the stack and adjust the spacer thickness to have the correct radial dimension. At the innermost radius, we have a 20 micron one-side aluminized mirror foil to separate the beam volume from the sense wire volumes. The beam volume is filled with the pure helium, while we have the gas mixture in the sensitive volume. As you can imagine, we work at the atmospheric pressure, and the gas system is able to maintain a few Pascal the pressure of the drift chamber above the atmospheric pressure. You can see on top right image that we have some extensions connected at the innermost radius of the drift chamber, because this chamber is part of the MEG2 beam line with the target at the center. So we have this extension to be connected to the MEG beam line. And then we have the external carbon fiber mechanical structure with the structural gas tightened function. And the mechanics proved to be stable at the micron level and adequate to sustain a full run of MEG2. Then a brief introduction to the front-end electronics. We have 216 front-end boards per side with differential channel to the radio signal for 8 drift cells. We have a double amplification stage, and the front-end feature also a high bandwidth of nearly 400 megahertz. The signal readout is made at both the drift chamber sides to help the reconstruction of the Z coordinate with the time difference and charge division methods, and the high voltage is supplied from the upstream side. You can see a picture of the, one front-end card here with the input connector connected to the anode PCB tails, and the coupling capacitor at the gain stage, while the output connector and the voltage stage is on the bottom side. The end caps you can see here is very crowded, and so we have a cooling system embedded in the board holders to keep the temperature under control. And we also have a continuous dry air flushing inside the end plates to avoid the water condensation on the electronics. Talking about the working point, here you can see that the working point is defined as the voltage to have a gas gain of 5 times 10 to the 5, and we perform Garfield simulation on single reactor gain to obtain these curves. And you can see on the bottom the table summarizing the average working point in high voltage as a function of the layer. And this tuning of 10 volts per layer is used to compensate for the variable drift cell dimension with radius and with Z. And about the electrostatic stability, we perform first a very simple test with 2 meters long 3-wire prototype at the Meg lab. Here you can see in this interesting plot the uncut distance as a function of the voltage. You can see the drift chamber working point and the border of the electrostatic stability, which is constant regardless of the overall 3 wires mechanical tension, of course increasing the voltage. And giving the modular assembly, we performed also a systematic voltage test at different length, and so wire elongation at PSI in a clean room, and this is done to adjust the length and find the final lengthening of the chamber experimentally. And the final length is set to 65% of the elastic limit. Here, just a couple of pictures of the detector integrated in the Meg 2 apparatus. So we have the chamber hanged to the superconducting magnet, and here you can see all the signal voltage and cooling and dry air circuits connected, and also the gas inlet and outlet for the gas mixture. Now, talking about the problems we encountered along the path, this is just one slide, but behind this slide there is a lot of work, I can say. So we experienced the breaking of 107 aluminum wire, especially the 40 micron wire in presence of humidity. You can see here some SEM images of the breaking point. And we developed a safe procedure to remove all these wire segments that you can imagine can put to ground a big portion of the chamber. And actually we did it, so we successfully removed all the broken wire and eliminated also possible damaged wires by extra stretching the chamber, and then went back to the working length. And keeping the wires volume in inert atmosphere helped to not have more broken wires due to corrosion. And another problem is about the anomalously high currents we experienced in 2019. This was probably triggered by an accidental anode cathode short circuit during the run. Essentially, we found, by reopening the chamber, we found a very short segment pointing to another wire. And this was probably due to an old broken wire not spotted during this campaign to remove the wire. And so we deeply investigated this problem, so we as I said, we reopen the chamber and we close it in a transparent plexiglass shell to directly spot the discharges in the chamber. And this is a picture of these faint point-like lights in a dark room. And this was due to coronal light discharges. And these coronal light discharges were found in correspondence of 6 whitish regions. Actually, it was not easy to spot them, but with the correct light in a dark room, you can highlight this. And okay, we faced this problem and we fully cured the problem with additives in the gas mixture. In particular, the oxygen proved to be effective in reducing the high currents, and also the isopropanol is crucial to keep the current level stable. Here you can see the conditioning period of the chamber at the start of the data taking run. You can see that the first part, in the first part we have high current and high oxygen level, and then we end up with the final oxygen level and a good stable current. Here you can see just the current of the chamber as a function of the muon beam rate. You can see that the current followed reasonably well the beam intensity up to intensities never reached before. The working point of Meg is here in the middle. And you can see also that the gas gain is also sensitive to the variation of the atmospheric pressure. Then just a few slides about the data taking. Here you can see the occupancy of the chamber with the full two-third readout, two-third because we have the C-shape acceptance here highlighted on the right. Here you can see a typical waveform acquired with the front-end boards. And I want to stress that the 2021 run was the first year with the full two-third readout. Here you can see the correct scaling of the occupancy by layer as expected with Michel, Positon, event. We have a good uniformity between layers. With the, this is a sign that the 10-volt scaling works well. And we also measure the gain on data based on the signal amplitude distribution for cosmic ray events. And this is because we exploit a cleaner environment without pileup. And the gas gain the measured gas gain is in agreement with the expectation. So just a plot in the transverse plane of the reconstructed heat. And all these plots are preliminary because the data analysis and continuous development are ongoing. You can see here the calibration of the Z reconstruction. You can see the track C versus the 8Z, and where the 8Z is measured from time different and charge division methods. And we can see also the distribution of the 8-track residual with improved configuration of the reconstruction. We are now at the 140 micron level. Before concluding, you can see here nice straight track from cosmic rays and one Michel Positon track. And here there is a sketch of our 3D visualizer with the heat in the chamber. The green heats are in the chamber. And the table on the right summarizes the current performance based on data. So coming to the conclusion, the new drift chamber of the Meg experiment has been presented. Here we have the highlights of the chamber. Despite the COVID-19 situation, we were able to perform especially the 2020 and 2021 commissioning period at PIsa of all the sub-detector. And now we hope, all the group hope that we enter a very exciting period of data taking. We encountered several problems along the path, but we faced and we defeat them. And here you can see the final Meg sensitivity compared to the one achieved with just 2 months of physics data taking this year, and just the projection with the 2022 data taking here. And okay, that's all from my side. This is just an invitation to go to the posters. Thank you.
Thank you, Marco. So we have time for one question. Okay, we have two. Let's try to go fast.
Do you understand the mechanism of this wire corrosion due to humidity?
Yes, actually it was a galvanic corrosion of the aluminum core caused by the silver plating. And the silver plating, the silver and the aluminum core undergo a galvanic corrosion, essentially.
Yeah, it's quick about this whitish thing cured by oxygen. Have you checked the material? In CDF many years ago, almost 20 years ago, we experienced that hydrocarbon was growing in an unexpected way very quickly, and it was cured by adding 100 parts per million of oxygen, more or less, of oxygen, and then cleaned up the hydrocarbon.
Yeah, actually we were able to remove one cathode wire from passing from these regions. Maybe I have something in the backup. Just a second, sorry. A long backup, but it's a lot of work, I would say. Yeah. Okay, this one. Yeah. Essentially, the most strange component we found is sulfur here, but we didn't explain this. Maybe an outgassing of the wire PCBs due to the shorts I said before. Sorry? Maybe.
Okay.
Okay. Thanks. We have to move ahead. Very interesting and very important, this problem of wire corrosion. Let's thank the speaker again. So next speaker is Ioannis. Did I pronounce correctly? Yes. It's a very interesting talk about the spherical proportional counter for neutron spectroscopy.
Okay, thank you for the introduction. I'm Yannis Manthos, as mentioned, from the University of Birmingham, and I will talk to you about the efforts that we do for neutron spectroscopy with the spherical proportional counter. The motivation about neutron spectroscopy is well defined and interdisciplinary, but as we are physicists, we care about physics. And as a matter of fact, in dark matter underground experiments, the remaining cosmic ray flux and the radioactivity of the cavern is giving us MEV neutrons that mimic the WIMP signals, being in the same region of interest with the dark matter detection. Of course, we can reject these neutrons with shielding and the use of high radio purity materials, but it would be very beneficial and of extremely interest to have an in-situ measurement of the neutron background at the underground labs in order to compare with the observed number of events. The state of the art at the moment is the helium-3 proportional counters that have many advantages. They are very efficient, especially for thermal neutrons, and they have low efficiency in gamma rays, but they have the disadvantage to present the wall effect. Wall effect is when the recalling particles are escaping the volume of the detector, so we lose the spectroscopic information about the energy. And the other disadvantage is that helium-3 has become extremely expensive during the last year because of the scarcity of helium-3. So what we propose is the use of the spherical proportional counter, and on this slide I will give some insights of the detector, which is a quite simple setup based on the spherical geometry, as the name implies, that the metallic vessel serves as the cathode, it's grounded, and in the middle an anode, a small anode, supported by a metallic rod through which the high voltage is supplied. The main characteristic of this detector is the big difference between the radius of the cathode and the anode. And this makes the electric field to scale as 1/r square and divides the field into the drift and the amplification region. Again, due to the big difference between the radius of the cathode and the anode, the capacitance becomes independent of the detector size. So we have very low capacitance independent of the size of our detector, and this makes the detector be very quiet, low electronic noise, and we can detect even single electron events. It's quite simple setup, robust, and we can operate at sustained high pressures, and has several applications from neutron spectroscopy to dark matter searches. And as a matter of fact, in Snow Lab in Canada, the new G collaborator has chosen the Spherical Propulsion calendar for the dark matter searches that we do there. We propose we say that if we fill our detector with nitrogen, we can detect neutrons, and this has some advantages. First of all, it's not toxic, not flammable, it's easy to deploy and operate even in an underground lab that we need remote operation. And of course, both the sphere and the Spherical Propulsion counter and the nitrogen are cost efficient. By this way, we aim to suppress the wall effect due to the higher atomic number of nitrogen, and to be able to do spectroscopic measurements of neutrons by taking into advantage these two reactions with the nitrogen and neutrons. The first one is giving protons and is more preferable for thermal neutrons. As you can see here, it's this part magnified in this inset plot. And the second one reaction is giving us alphas, and this has comparable cross sections. This reaction is with green and has comparable cross sections with a helium-3 that it is with blue in this plot. So by taking into account that we can operate with larger target masses, we say that this method is a quite nice alternative to the helium-3 detectors. A partial proof of principle was given some years ago by some colleague of us in Csec, that they managed to detect, this is the americium beryllium spectrum, and this is what they detect. So they detected fast neutrons, indeed, but there were some limiting factors due to the constraints in the instrumentation of the detector at that moment that resulted on the wall effect to be apparent, and also they couldn't operate higher than half bar. So this resulted to very high voltage that had problems of sparking and stability of the detectors. Also, some impurities were not metallized, and this resulted in poor charge collection efficiency. What we are trying to do now is to incorporate the instrumentation advancements of the Spherical Propulsion counter, with most important to be the resistive multi-anode sensor. We call it achinos, and achinos means in Greek, it's a Greek name for sea urchin, and you can see the similarity. And this is the sensor that we use, which is an 11-anode sensor that has the advantage that decouples the drift and amplification field. And what I mean with this is that the drift field is determined by the virtual sphere that these balls are forming. So we can have bigger radius of this virtual sphere, and we can have higher drift voltage, so to avoid recombination. And the amplification field is defined by the radius of these small balls, so we don't have to go to extremely high amplification factors and to have sparking of our detector. So this makes the detector more stable, and we can operate at larger volumes and higher pressures. Also, it gives us some kind of fiducialization of the detector, because we can read with different electrodes each ball. For the moment, we read with two electrodes, the upper part and the lower part of the sensor, but we have plans to go even with 60 balls, so you can operate like TPC, not TPC, but like TPC. The second advancement that we have is that we have introduced gas purification systems that remove the impurities of water and oxygen from the nitrogen that we use, and this improves the gain of the detector. And also we realized that the commercial filters emanate radon, so we have developed a custom-made filter with cooperation with the University of Liverpool that does not emanate any radon anymore. very important tool that we have in our hands is that we have the simulation framework at the University of Birmingham that combines the strengths of JAMP4, ANSYS, and Graphical++ simulation programs. And we can simulate the complete detector setup. And here are some examples of the simulation that we can see some thermal neutrons at the nitrogen, that we can see the response of our detector to these thermal neutrons, and also the simulation result of the fast neutrons at 4 MeV, for example, here, that we can see the tracks of the alphas and the protons between the two reactions. So we can differentiate protons from alphas by the use of the simulation. And also, we can identify if we have any possible wall effect at the pressure that we want to operate. The results that I will show you are investigating the capability of the spherical propulsion counter to fast and neutrons thermalized by the graphite stack facility that we have here in the University of Birmingham. This is our sphere, a 30 centimeter spherical propulsion counter filled with nitrogen and equipped with the 11 anode Achinose detector that you saw in the previous slide. We used an americium beryllium source and to have neutrons that we thermalized with the graphite stack facility that you can see here. The setup is quite simple. As I told you, this detector is quite simple. The high voltage is provided through the preamplifier. The signal is read by the preamplifier. It's digitized, and we do the data acquisition and the analysis on the PC that it is there. This is what measurements we did at the graphite stack facilities, of course, calibration and measurements of thermal and some measurements of fast neutrons at various pressures and bias voltages. Of course, before we start, we had to do a calibration, and here we have, which we had the opportunity to have two means in order to do the calibration. The first was with a polonium-210 source inside the detector that gives us alpha sub 5.4 MeV. This is the amplitude curves that we have. It's a very nice exponential curve here, as you can see, and this gave us the opportunity to choose the operating voltage in order to have the dynamic range to detect the thermal neutrons. The second mean of calibration that we had, it's a disadvantage that, as I told you, the commercial filter was emanating radon, but we can use this radon to have a direct calibration and direct reference of the energy inside our detector. And you can see here, indeed, the three radon chain peaks that we have here. Also, we confirmed the radon decay rate with an accuracy of 3% with doing consecutive measurements in 2 days. This is a typical pulse of the spherical propulsion counter. It's quite slow compared to micromegas or other gaseous detectors. It has a duration of some milliseconds and a rise time of some tenths of microseconds. And this is, of course, we used the standard pulse shape analysis parameters. We checked everything to do our signal analysis. And we realized that if we do just some soft cuts on the rise time and the width, you can see here the raw data that we can have. If we just apply 2 soft cuts on this, we go there, that the mostly electronic noise that is here is diminished very, very much. And here we demonstrate the detection of thermal neutrons at 1 bar and 3.6 kilovolt and the anode of the detector, that it is here, the rise time versus amplitude, pulse amplitude scatter plot, that the radon decay chain confirms the thermal peak in terms of energy, and this is a Gaussian peak that we have for the thermal neutrons. And this plot compiles the measurements that we did at various anode voltages at 1 bar, that you can see that the detector indeed is proportional. It's fitted with a very nice exponential. As I told, we had the opportunity to do simulations, so to use our simulation framework. So we have here the detector response to the thermal neutrons at the conditions that we did the experimental measurements. And you can see here, indeed, we can have the thermal neutrons. We can see if we have a wall effect, which was very negligible. And here we can see that we have a neutron capture in the vessel that, of course, we don't see on the experimental data, or we don't see most of this because of the trigger that we set here. The other thing that we have according to simulation is that we had the opportunity to calculate the probability of each neutron to reach the detector volume after thermalizing the graphite stack. And by combining this information with the activity of the source and the detection rate that we had, we concluded to an estimation of the efficiency that is 3.7 10 to the minus 4. which is in a quite good agreement with the simulation results that give 2.2 10 to the minus 4. Here we demonstrate the neutron detection at 1.5 bar. Again, it's thermal neutron peaks here, confirmed by the radon peak, the radon decay chain. I don't want to spend too much time on this. I want just to say that in this pressure, we had the opportunity to do fast neutron measurements that we see it's a very clear distribution here. Of course, this is the radon peaks, which is where apparent. And of course, you don't see the americium-beryllium spectrum because the unfolding of the signal is needed. That I will talk about this later on. And this is the record pressure that we managed to operate at 1.8 bar at 6 kilovolt. It's a very demanding measurement, this, that we managed to confirm the thermal neutrons that we detected here. And in this measurement, we didn't use a commercial filter. We used a custom-made filter that does not emanate any radon. So we, for energy reference, we put inside the detector a polonium-210 source, and you can see here that this confirms the thermal neutrons in terms of energy. And also, I forgot to remind that thermal neutrons, the reaction, what we detect is the recoil energy of 625 kV, and not the real, the 0.0025 EV of the thermal neutrons. The next step was to do more measurements of fast neutrons, and we had the opportunity to do this in the cyclotron facility that we have in the University of Birmingham, that provided us with 5.9 MeV deuterons. We put a target, a beryllium target, in front of the beam line, and with the same detector setup, we detected the fast neutrons. Of course, you use moderators to study the neutron detection and to confirm that those are indeed neutrons, like paraffin, boron-doped polyethylene, and despite not being a moderator, lead as well, and you will see why. And this is the results that we have. You can see that on black we have the fast neutrons, and the green is the effect of the paraffin, that of course it's thermalizing, and we have a very clear thermal neutron peak here. And when we use polyethylene, it's just even this thermal neutron peak is absorbed by the boron that it is doped in the polyethylene. We used lead as well, but as I told, it's very well known that it's not a moderator. But what you can see here, it's not thermalizing, so the shape of the spectrum is exactly the same. But what it does, because of scattering of the beam line, it just reduces the rate of the detector. And here in this part, we are noise dominated by the cyclotron. What makes us very happy about this measurement is the comparison with the simulation that you can see here on black, the experimental data, and on colors, the simulation, which is in a very, very good agreement between the experimental, between them. And the simulation gives us the opportunity to look under the hood of the data and see the origin of each event and what interaction is responsible for what we see on our detector. Of course, this is an ongoing analysis, and we want to extract more information about this. What we're doing now, that we are in the next step, we have the opportunity to have a similar detector, an identical detector, like the one we have in Birmingham in the Bulby Underground Lab, which is a mine 1,100 meters under the surface of Earth at the North Yorkshire in North England. And there, with a similar detector, we have a californium neutron source available, and we try to detect fast neutrons there, which is a very demanding measurements. The conditions in a mine underground are different like the lab. We have already some measurements, and the analysis is ongoing, but our goal, of course, is to measure the neutron background there in the Bulby mine. And we have done some calculations that if we thermalize the neutrons in order to have, for first step, higher cross-section, we can see that with a slightly bigger detector than the one we have numbers that are detectable by our detector. And also summarizing, I show you that we successfully detect fast and thermal neutrons in Birmingham in the graphite stack and cyclotron facilities. The measurements at Bulby are ongoing. And in order to do the unfolding of the signals, the next step is to do more energetic neutron measurements. There is a facility in Greece that can provide us this neutron beam that we try to arrange this. Of course, you understand that COVID and Brexit is not good for us, but we will try to overcome these difficulties. Thank you for your attention.
Thank you. Very nice project. Are there questions?
Thank you for the talk. Can you go at slide 17 or so? You write the energy of the thermos around 1 MeV.
It's not 1 MeV, it's 625 keV, and it is the recoil energy of the reaction that give us the protons. That is what we detect at the end.
Okay, so the lower energy part of the thermal that you are not so efficient in detecting, or?
We don't have, with this method that we use, we don't have access to this part of the energy because the reaction gives us the 625 kV.
But when they are moderated, they are shifted towards the very low energy side. That's why you, the black points, they are the simulation, right?
The black points are the data.
And at very low energy, you have some discrepancy.
Here, yes, I have a discrepancy, but it is here. We did a background measurements at the cyclotron, and we realized that the cyclotron is still giving particles, despite without even neutron deuterium beamline.
Okay, because on the left there is no energy, so I was kind of wondering where this gray line is on the right plot. Now I see it. Okay. Okay, thank you.
Okay.
Other question? Me, I have one curiosity. How did you choose the 11 anodes? Why 11?
Because it's symmetric. And the next step is the 60, because again it's symmetric. 60 is the edges of the football ball. So it's to have something that is symmetric.
Okay. So next step is 60. You will try with 60.
Yes.
Okay. Thanks. So let's thank the speaker again. So next speaker is Gianfranco. So we come back to LHC, especially for the phase 2 upgrade of the LHC muon system.
Oh, good morning, everyone. And thank you for the invitation, but let me also welcome to this talk, because today we had talk about ALICE, about CMS, now it's LHCb moment. This is a detector who achieved excellent results for the physics for which it was drawn, but also for something more, because you know, when you can find always something in the jungle of exotic hadrons. I want to express my gratefulness to all the colleagues who earlier in this conference had already described the upgrade of LHCb, so that I can save my time. Actually, I'm using for thank them. I also listened very nice talk about the upgrades of the systems. But since I'm talking about the muon system, you can easily understand of what we will talk about. A system who really worked in an excellent way during the run 1 and run 2, even if it with a in a very harsh environment, and with ensuring a very low level of inefficiency. Now that the luminosity will increase, we need something that can stand up to 1 megahertz per square centimeters, ensuring anyway an efficiency of 95% in a time window of 25 nanoseconds with a good granularity. And of course, you want something stable. You don't want to change them every now and then. So, and also, of course, something that is cost effective, because, okay, you have to cover up to 90 square meters. Practically, the collaboration is asking for a perfect detector, but we live in the real world. And what we can propose here is a microresistive well technology. Okay, here I want to spend a few seconds. In this conference, someone reported a wrong version of this picture. I apologize. I did this sketch, it was my mistake. I beg you, if you need this picture in the future, take from here, please. The mistake was simple. I didn't. Errata. Okay. Okay, it was just here. In the previous version, I put a diode while the real sketch, the real one, you need here a front-end electronics. It's just a detail, the rest is okay, because this is a sketch reporting that you have a resistive PCB board with a resistive layer that you introduce to quench the sparse amplitude, and the amplification stage that is patterned like, that is inspired to well geometry, and it's patterned like gems. And it's realized with chemical etching, a well-established technique to manufacture the detector. I can say well-established because it's more or less 25 years of gems. As you introduce a resistive layer, you have a drawback because you have a gain drop as you increase the rate of your radiation. We propose in this paper an if model for this gain drop where we introduced some parameters, but the real parameter on which I would like to focus your attention is this D that is related to the geometry of the detector. The rest is something that does not depend directly on the detector. So, based on this parameter, I can show you the evolution of this detector. This is the simplest layout with a grounding all around the active area that can stand up to 100 kilohertz per square centimeters. We wanted to create something more performing in these terms. We introduced a double resistive layer that can stand at very high rates. We measure this at PSI. But this is complex manufacturing. We have so to step back to something simple with a single DLC layer and some grounding lines below this DLC. But for this, to avoid the discharges, we had to introduce that area, and that area must be aligned with these grounding strips. And when you move to large scales, this can be quite difficult. So we keep the one single DLC layer, but the grounding is not produced below, but just above. Because when you pattern the amplification holes, you can also pattern a groove. You can plate this groove, and then you can connect the DLC to grounding. Now, think a bit. We are realizing a modular active area. If you think that each module is delimited by 2 grounding grooves. So, to validate this idea, you can irradiate one of these modules and check if the detector can stand up to a given rate. First, we try to shield the rest of the area with our PhD student hands, but unfortunately, you can understand it doesn't work. Then we moved to LED with an opening in the center, exposed to an X-ray with a changeable distance. And this is to show you that in this area, the radiation was nearly uniform. And we measure our rate capability. I mean the gain drop. We decided to choose rate capability, to define the rate capability as that rate where our detector loses the 10% of the gain. I would like to point out that if you, and I guess all of you, chooses a good point on the plateau of efficiency, if you lose 10% of the gain, does not affect really your efficiency. Anyway, here with this prototype in argon CO2 CI4, we could not reach this drop. Here I'm reporting not only the X-ray flux, but a conversion to MIP flux. This is easily computable, taking into account the ionization of the particles. Okay, I told you argon CO2 CF4, but we had a nice exchange this morning between Silvia and Daniele. We all know that we have to move to some eco-friendly gases. So we changed our mixture to argon CO2 isobutane, and we started a stability measurement. In fewer than 15 days, we monitored the current and we monitored the average. We, of course, controlled the parameters of the temperature and pressure to apply the corrections at this rate, 550 kilohertz per square centimeters. At this point, after, let's say, 14 days here, the T0 is 2. We integrated something like 5 millicoulomb per square centimeter. We need to reach this value, 1 coulomb per square centimeters. That corresponds 10 years, so at LHCb at this MIP rate. The average of these parts, the trend of the average matches with the trend of the T over P for these 3 different regions. Okay, here I have to show you some old time measurements on the time resolutions because we are planning to make them in the future. In the past, with the argon CO2 CF4 and the VFAT2 front end, we reached the limit of about 6 nanoseconds, but you see a saturation of the front end, and anyway working at a very high gain. This means that you can't use this front end, and there's something to be done. We are using a new front end, and our colleagues in Bari, they are working on it. The FATIC has been introduced last Wednesday by Anna Stamerra. The new front end has an adjustable peaking time from 25 to 100 seconds, and in order to achieve a good time resolution, but if you use also majority logic, you can improve. Anyway, the measurements will be done in the near future. Okay, let's go back to slide 2 and 8, recalling some numbers. The number of detectors we need to replace the innermost region of the muon stations, the area to be covered, and of course, we can do this work by ourselves. We need companies. We started a transfer technology. This looks like a board game, but it should be easy to follow. We had contact with Eltos for PCB production, who receives the DLC foils, create the stack of the PCB, sent to CERN for the chemical etching for the final manufacturing. And then the detectors are sent back to Frascati. Here I would like to point out that, thank you, so soon the DLC foils will be produced at CERN thanks to a machine that is bought, confounded by Gruppo Uno of INFN. So here you can see that a technological transfer can be done even from industry to research. So there's a very nice exchange. And this should speed up the production of the DLC and the speed up of all the detectors. Okay, I hope I convinced you that this technology is suitable for the upgrade of the muon station of LHCb, thanks to the new grounding network layout, and thanks to the front end that is being developed by our colleagues in Bari, and thanks also to the collaboration with industry. Of course, a lot of work must be done yet, focusing our attention to eco-gas mixture. We are planning a slice test in LHCb. we are planning some mechanical improvement of some detector component. I would like to finish with this slide to show you that this technology is involved in other projects like FCCEE, and I invite you to visit the poster of Riccardo Farinelli. I have to apologize with the collaboration class 12 for this typo, but for me they deserve a double S. Also, if you haven't been trapped by Matteo last Tuesday, there was a poster about neutron detection with this technology. And also, I think you remember that also Anna cited this technology for the muon collider, for the hadron calorimeter of the muon collider. Thank you.
Thank you, Gianfranco. So big challenges in front of us. Are there questions? I have one to start. Is about the change of the gas mixture. Isobutane is a very good quencher, but it's not timing properties. How do you think you will manage to get a very good time resolution with this gas mixture?
Oh, okay. I agree with you. First, I would like to make some measurements, first of all. I told you that we are developing a front end, and to achieve the final time resolution, I have to remind you that we are working with 4 detectors in OR, and this should help a lot. Then, of course, there's an intrinsic limitation on these mixtures that, honestly, I haven't simulated yet. I need to. I had to prepare the slide for the conference, and I will do as soon as I will go back to my office.
Okay, thanks. Other questions? Okay.
If not, I would like to. I need just a few seconds more. Some of these projects had the contribution of a person who passed away about 1 year ago. Since this is the first detector conference held in person since that terrible day, I would like, if you can allow me, to mention a friend and a colleague, Stefano Cerioni. Thank you. That's all.
Thank you. Okay, next speaker is Mariana, that we speak about high rate, high granularity, timing, multi-strip, multi-gap, resistive plate chamber. On the other way around.
Thank you. This is pointer. Okay, thank you very much. Yeah. Good morning, everybody. I am Mariana Petris from National Institute of Physics and Nuclear Engineering from Bucharest. I would like to thank the organizer that gave us the possibility to present our R&D activity dedicated to the development of a high counting rate, high granularity, multi-gap resistive plate counter with multi-strip readouts. The outline of my talk starts with the motivation, and I will let you know construction details and in-house laboratory results of the results of the in-house test that we performed with the assembly prototype. And also I will continue with the results of the in-beam test performed at SIS-18 accelerator of GSI Darmstadt, including high counting rate test of this prototype. Second part is dedicated to aging investigation that we have done using high activity cobalt source that we have in Bucharest, and I will detail a few of the observed effects, and I will end the talk with the mitigation that we propose for the observed effect, which is a prototype with a directed gas flow through the gas gaps. We assembled it and tested it at SIS 18 accelerator of GSI Darmstadt, and I will end with a summary of the main results and an outlook of the next activities. Among the experiments that are going to explore the phase diagram of QCD matter at high net baryon densities, compressed baryonic matter experiment is designed to run at unprecedented interaction rates of the order of 10 to 7 interactions per second. For this reason, it will be equipped with fast and radiation hard detectors read out by a self-triggered front-end electronics and a free streaming data acquisition system. I would like to underline here that it comprises a time-of-flight sub-detector, which is based on multi-gap resistive plate counters with multi-strip readout, part of them equipped with a low resistivity glass in order to cope with the high counting rate anticipated for the surface of the top wall, which could reach in the most inner region up to 50 kHz per square centimeter, the requirements being to keep the system performance in terms of time resolution, system time resolution, and efficiency up to these unprecedented high counting rates which the RPC developed until now hardly could cope. Our R&D activity was dedicated to the most challenging region where we have the highest counting rate and the highest granularity. And on this slide you can see the design of our prototype, which is a symmetric double stack structure with 5 gaps per stack with 200 micron gas gap thickness and an active area which is defined by the strip length and the maximum available size of the low resistivity glass that we used for the resistive electrodes. We have a strip structure for both readout and high voltage electrode, and I will come back to this in the next slide. And the counter has a differential readout, both the negative and the positive signal being fed into the input of a readout channel. For a free streaming readout, is mandatory that the signal transmission line to be matched to the input of the front-end electronics channel and of the readout channel. And in our case, due to this unique architecture of the electrodes, we allow to adjust independently the granularity and the impedance of the transmission line, which for a given number, for a inner geometry of a counter already fixed is not a trivial thing, and especially for double stack structures. We have the same pitch for both high voltage and readout electrode, and the granularity is defined by the strip length and the strip pitch. In order to get the signal transmission, the desired signal transmission line impedance, which depends on the width of the readout strip and the dielectric properties and thickness of the material in between the anode and cathode readout strips. We used Aplax simulations, and we obtained 1.3 millimeter width for the readout strip in order to match the input of the input impedance of the front-end electronics. You can see here that in the simulation, the output signals nicely reproduce the input signals without any distortion, and we will see later on that we got this also in reality. On this slide, you can see how looks the components that are used for assembling the counter, and we have here the high voltage electrode, the readout electrode, the spacer distributed across the low resistivity glass, and the two stacks of a counter assembled together. Two such counters were installed on the back panel of a gas-tight and electromagnetically screened housing box. And we have all the services on this back panel, high voltage connector, gas connectors, and connectors for the front-end electronics. The detector was transported in laboratory. It was flushed with this gas mixture, typically used for RPCs. And you see here the first signals that we recorded directly from one end of a strip. We read out the strips at both ends. And on a time scale of 25 nanoseconds, we have not seen any reflection. And the dark current and the dark rate were very low for these counters. In laboratory, we positioned them in an experimental setup and scanned the active area using a cobalt source positioned at a certain distance under the counter in such a way that we illuminate it uniformly, the active area. And as you can see, we don't we have sharp edges and uniform heat detection over the active area. And we perform the same using cosmic rays in order to be sure that we don't hide anything with the activity of the source, and the results looked similar. We got efficiency plateau around 96%, and the time resolution single counter of the order of 67 picoseconds using cosmic rays. Later on, we installed the counter in the mini CBM setup, which is a CBM prototype test setup dedicated to testing the readout chain and online and offline analysis for CBM, but in the same time it is dedicated to perform high counting rate tests for the detector prototype that we developed. And it was positioned in the, let's call this, it's called mini-TOF because mini CBM comprises detectors of all detector types that are will be later on installed in CBM. And we are here in the mini-TOF and equipped the detector with the front-end electronics that was developed for special for the inner roll, having the amplifier discriminator and the GET40 DC integrated on the same board. We configured in the mini-TOF a tracking setup with C station. One of the and in the analysis, one of the station was detector under test, and the other 5 were used as reference. And here you see that we nicely reproduced the efficiency that we measured in the laboratory with cosmic rays. We have a cluster size of the order of 1.7, 1.8 strip per hit, and the time resolution which reached up to 45 picosecond single counter time resolution. Scan with the beam intensity was translated in counting rate, and here you see how nicely the detector reproduced the spiral shape with a peak at 30 kilohertz per square centimeter. This shows qualitatively the counter performance in counting rate. However, the quantitative one is shown here, which show that the efficiency doesn't decrease significantly as a function of counting rate, and also the time resolution still stay at 50 picoseconds at the highest measured counting rate. And the spectrum, the time spectrum that we from which we extracted the time resolution has still a nice Gaussian shape at the highest measured counting rate. In parallel with this test, we performed aging investigation motivated by the fact that we would like that the detector to maintain its performance over the lifetime of the experiment. And we used for this our facility that our institute with a cobalt source of 360 kilocurie, very intense source. We positioned the detector in front of the source, and we monitored the current accumulating over successive period 35 coulombs and a dose of 30 kilogray, which, and if we divide with the active area of the detector, we will got an accumulated charge equivalent of 4.13 coulomb per centimeter per square centimeter. From knowing the rate and the current from an in-beam test, we were able to make a rough estimation of the equivalent particle flux, and we using this the measured currents, and the range was up to 300 kilohertz per square centimeter, which is 10 times more than we expect in the CBM inner zone of the CBM TOF. We monitor the current at different gas flow, and as it was expected, the slope of the increase of the current is lower for a higher gas flow, and also the recovery in the short period of time between two successive exposures is much faster if the gas flow is higher. At the end of the irradiation, we transported the detector in the laboratory, and we monitored the dark current and the dark rate, and after 2 weeks we got almost the same value as before the exposure. The efficiency doesn't change significantly, but the cluster size has almost 25% decrease. What we observed is that around the spacer that were positioned in the gap between two strips, we had a high activity, high dark rate, which was much more concentrated on the middle, and the lower toward the edges of the counter, and this was associated with the speed of the exchange of the gas at the edges in comparison with the center of the counter. We observed this white deposition around the spacers, and also this colorful deposition on the two sides of the low resistivity glass. The one on the anode could be removed with the solvent. The other one was not possible, just scratch with a scalpel and getting this white powder. We used many analysis methods to investigate this deposition. Here is exemplified only with EDX, and these are the results that we got for the irradiated gas plates, where the floor is the element that is discovered in this deposition, and it was not existing in the non-irradiated glass plates. We can observe also change in the concentration of the oxygen, and all these were associated with gas pollution effect, obviously, and we have been thinking to find a solution to this, and the solution was to assemble a prototype with a directed gas flow in order to keep the surface of the glass plate as clean as possible, and to delay and to mitigate this effect. We designed this gas guider, which were positioned at the end of each stack for input and output. As you can see here, here you see the prototype assembled having the input of the gas in the two stacks, and at the output of the two stacks we got equal flow from both of them. We conditioned the counter in the laboratory, and we got nice signals as for previous one, and we tested it in beam. In the mini CBM setup, you see here the heat position across the full surface active area of the detector. It reflects the position of the counter relative to the beam direction. You see here the time over threshold distribution without any reflection, and an average cluster size that is almost the same with the one measured for the previous prototype with gas exchange via diffusion. This is the working curve that is similar with the one that we measured for the previous prototypes, and we got a single counter time resolution of 51 picoseconds. the high counting rate. In the high counting rate test again, we can see this nice reproduction of the spill shape. We speak at this time of 20 kilohertz per centimeter, where we had a single counter time resolution of 55 picoseconds. Fortunately, because the other counters which were in the tracking setup were not counting the performance, and the efficiency was not possible to be accurately estimated this time. We had another test in March this year, and we hope that we will cover also this with the results, with the data that we took in this in-beam test. But coming to a summary of what I presented, I would like to underline that our prototypes proves very good efficiency and time resolution in the laboratory, in-house test as well as the in-beam test, and performed in high counting rate. We performed aging tests that showed an important gas pollution effect, which could limit the lifetime, and we proposed a mitigation solution, which is the prototype with a directed gas flow. We are aware about the much stronger dose rate to which we expose the counter in a shorter time, and we plan to repeat this aging test at lower dose rate and longer exposure time. And we are working to design a counter with directed gas flow wider than the one that I showed you. Thank you.
Thank you, Mariana. So I think this aging problem is a very hot topic in this session and really need to be addressed by the community. Are there questions?
Can I have one, Beatrice?
Yes, absolutely, Max.
Yeah, I just would like to mention, thank you very much for this very interesting results. But for your final prototype, do you consider to have a very careful evaluation or measurement of the water content? Because having your gas together with water might, in addition to the effect that you observe, lead to the very strong catching effect. It's known that HF is very aggressive against the glass. And once there is a significant amount of humidity, you might, in addition to this, have a very strong catching effect, even if you run in the continuous mode without recirculation.
Yes, we are aware about this. We in our future test of aging, we plan to be much more careful concerning this issue. And in the experiment, in the final experiment in CBM, we will have these metallic pipes which will transport the gas, and we will take care of this issue, obviously.
Thank you.
Thanks. Yes, I have the same comment about water content. So, any other question? Okay. If not, let's thank the speaker again. Thank you. And let's move to the last talk. So we started with TPC, and we conclude with TPC for the T2K experiment with Gianmaria.
Okay, good morning. It's a pleasure to be here and to illustrate to so many friends and colleagues, to illustrate the new TPCs that we are building for the applicated near detector of the T2K experiment. So I would like to thank the organizing committee for this for the occasion. And I will, after a brief introduction about the upgrade and the T2K experiment, I will focus on the unique features of the new TPCs, which are related to the field cages and the sensors, the resistive micromega sensors for these TPCs. And then I will conclude with illustrating some most relevant performances. At the moment, we have performances measured with prototypes. So T2K is measuring neutrinos with two detectors. One is near, and one is the far, and which is super K, the superconductor detector. The near detector is measuring fluxes, energies, and contamination of nu E. But mostly we are concentrating on nu mu, which are then oscillating. And a new phase is going to start soon for addressing the measurement of the delta CP violation. And for this, we need in a near detector to reduce the systematics. And later, the ND280 will be used for the hyper K as near detector still. So systematics are mostly related to, the most important one is related to acceptance. You can see here a difference between the near detector acceptance for muons and the far detector, the super K detector acceptance for electrons. We are missing essentially high angle tracks, high angle leptons, and low energy hadrons in the near detector. So the idea for the upgrade was to add a new active scintillating target, which is made by 2 million centimeter cube scintillators crossed in the three directions by fibers, in order to have a three-dimensional reconstruction of the tracks in the target, and then two so-called high-angle TPCs, which are matching the tracks and measuring particle identification, momentum, and so on. So I will focus on these two TPCs, which are required to have momentum resolution within a magnetic field of 0.2 Tesla, the former UA1 magnet, huge magnet. So momentum resolution below 10% and 1 GeV. 1 GeV is the energy on average of neutrinos. And energy resolution for particle identification and tagging of muon against electrons below 10%. Space resolution better than half a millimeter. And in order to match the tracks against the neutrino target, very low, relatively low material budget against the scatterings and so on. So this can be solved by similar TPCs to what we have at the moment. They are vertical, so working at atmospheric pressure, slightly over pressure, in fact, in order to keep low contamination of oxygen and water at a level of few tens ppms. And still we are keeping the magic, let's say, and so called T2K mixer, mixing for considering the gas, which is very fast and low transverse diffusion. And we would like to have 80 centimeters of sampling length, and new detectors, which are resistive micromegas, which are allowing with larger paths to improve to have an improved resolution. And it's very important also to keep track deformations below the resolution. It's very important to have electric field uniformity at level of better than 10 to the minus 4 at a distance greater than 1 centimeter from the walls. So with this design parameters, we thought to new kind of field cages, which are essentially thin walls and low material budget, low density, and made entirely by solid electric composite materials, with this funny rectangular shape still, and with the mechanical accuracy in order to reach the proper electric field uniformity, with mechanical accuracy at a level of 0.2 of millimeter per meter, concerning planarity and parallelism of the flanges, planes, and internal planes. And of course, suitable electrode design. The second, let's say, unique feature is the detectors are in fact, let's say, resistive micromegas with the resistive plane embedded in the anode. They are called encapsulated resistive anode or ARAM. And thanks to charge spread, we reached, in fact, a very good resolution with the larger pads than we have at the moment. And in addition, we gained concerning spark protection, and so no protection circuits in the front-end electronics, and so more compact front-end electronics. So first, field cage, and then resistive micromegas. Concerning field cage, they are made in two parts with the central anode, so two halves with the central anode, central cathode, sorry, and two anodes which are reading out with 8 micromegas modules per anode. In one of the two half field cages are made, let's say, with these dimensions, so 1 meter drift distance, almost 2 meters in length, and 70 centimeters in height, and they are built by lamination process on a mold by composite materials. Yeah. So I also forgot to say that given the gas properties and 1 meter of drift distance, we have to work at almost 30 kilovolts for concerning the cathode. Now this is the structure of the walls, which is very important from many point of view. Essentially, we are starting from the inner part with electrodes. The electrodes are made by strips. There are two layers of strips staggered, one internal field strip layer and one external mirror strip layer. They are built on a Kapton foil, 50 microns, and on the back there is a protection made again by Kapton. This layer is very thin, and then they're starting the structural layers. So first of all, the aramid fiber fabric, which is Twaron, like Kevlar, let's say, 2 millimeters. Then honeycomb for giving a lever arm and to the mechanical structure, and then again the second peel, and finally again Kapton foil and the shielding, the external shielding. So the electrodes are designed, as I said, to keep a very uniform electric field up to 1 centimeter to the wall, and two are the very important points which were of our concern in the design phase. First, we have to use materials, including glues, which are the weakest point, in fact, materials which are very high resistivity. If you have an intermediate resistive layer in the wall, then it can be a nightmare, in fact, because the resistive layer will recharge, and it will draw a potential, and so draw charge from the anode and push charge back to the cathode. So you will have internal extra currents, and most importantly, the voltage drop will risk to provide dielectric breakdown. So this is the most important feature, and so we envisaged the use of glues, essentially, and also dielectric materials, which have very high volume or surface resistivity. The second point is the junction at the cathode side, at the cathode flange, let's say. The two halves are joined there, and for this, the thickness of the wall and the flange is too short for ensuring a proper voltage drop ratio to path length. So it's 5 centimeters, which are for degrading 30 kilovolts is too short. So we envisaged a kind of labyrinth, like in the high voltage connectors, by grooving, making machining grooves. One is the internally, let's say you can see the cross section here. One is, the first one is very deep, 3 centimeters, and then there are the two O-ring grooves, which are also quite deep. And this way, we keep the voltage drop to path length, let's say, below 3 kilovolts per centimeter, which is enough for ensuring that charge is not flowing or growing across the flange. So we tested the first point. We was tested with a full scale, let's say, transverse. Small transverse scale prototype and full drift length, so relatively large surface. And the second point was tested with dedicated mock-ups. This is the prototype. We also use it for measuring performances of the detector. I will discuss in the last part of the talk. And concerning then the most recent development of the project, we started to build the first half field cage. You see here the mold, which is produced by INFN with very high, let's say, level of tolerance, low level of tolerances, 1/10 of millimeter per meter in surface planarities and so on, because it has to be better than the chamber. And the first cage was produced by Nexus, the Nexus company in Barcelona. So you can see here some phases, the very long strip foils all around the mold, and then the phases layer after layer for constructing the cage. It's a huge cage, so it's quite complicated to manipulate. And here you can see the latest machining phase for providing the grooves. We have at CERN, we received at CERN recently the cage for validation. You can see from the cathode side and from the anode side. And there are 2 voltage dividers, and as I already told you, 2 O-rings which are custom and made in silicone. In fact, we started to test and validate. The metrology is very good concerning the tolerances and gas tightness also, and other mechanical tests were passed. Now the chamber is in, let's say, degassing in oven at 17 degrees, and then we will proceed with high voltage tests, and finally in September we will have commissioning and a test beam at CERN. Concerning iron detectors, this is a relatively old detector, but for this project, it was investigated in deep detail. Essentially, charge spread is providing an improved resolution, and so with larger paths, we had to use a low number of front-end channels. And in addition, we gained higher, let's say, higher gain and also protection for against sparks. Now, we are reading out essentially waveforms from the paths, which are helping to reconstructing the impact position of the single electrons or clusters impact point. And so you can see a sketch of the cross-section of the detector. You can see the mesh, the DLC foil, which is a resistivity of 400 kilo ohms per square. And with the combination, concerning the capacitance, with the combination of 75 microns of glue, we are reaching a proper level of, let's say, diffusion spread velocity. So at CERN, we started, in fact, the production of these detectors, a serious production, and it's important to stress that by a series of measurement, including mesh pulsing and X-ray qualification, we spotted a certain number of very important details that helped us to understand in very detail this kind of detector. And this has to be stressed. This is the first time we did. It was done for this kind of detector. So with mesh pulsing, we are able to measure essentially the capacitance mesh to DLC and DLC to pad. and to spot the irregularities there. And with X-rays, we are able to spot, let's say, even, let's say, micron level deformation of the mesh, because a few microns are corresponding to gain decrease of several percent. So we are sensitive to this, and we understood, and we, let's say, defined a proper procedure for gluing and preparing the detectors. Now, the detectors are very compact. You can see here not only the ARAM modules, but also the electronics, which is in parallel. And this is, let's say, the full readout is made in a few centimeters of few readout of one module, which is 1,200 parts. And the electronics is based on the old after chip, which is very good for sampling, and we didn't change it. You can see that at the moment within the project, the electronics is already produced, and the detectors are, let's say, 1/3 of the production. So you have here some figures, but essentially we are very well advanced with the production of the electronics, relatively well with the ARAM, and on certain field cases where we have 1/4, 1/2/4. Gas system is very important. We will renew it at J Park, and very soon this year will be installed. Some performances in order to conclude, just a few slides. With the prototype, 1 meter long, so full drift length and reduced transverse length in order to fit magnets at CERN and at DESI. We tested the performances of the detector. I will focus on the last year test beam at DESI with electrons, let's say a few GeV, within the superconductive magnet there. So you can see here one example of track with all the paths activated. There are primary paths and secondary paths. And we demonstrated the very well behavior of the very good behavior of the prototype concerning stability of the high voltage, gas contamination at a very low level, and stability of the performances in general. You can see an example here of, again, one track, primary path with the primary signal, which is bipolar, and according to Ramos, Shockley, and Maxwell, and here we have the information in the undershoot, very important, concerning the charge spread on the main path, and in the secondary paths we have information again of the charge diffusion. So we can not only reconstruct the track, but also with the large statistics, we can also measure the resistivity, or better, the RC constant for the DLC foil. I will skip the details. Essentially, for the spatial reconstruction, we have to build a path response function and to measure and fit tracks according to this, which is a standard method for this kind of path detectors. And with the path response function, we can measure very easily the resolution. So finally, the energy resolution, the X resolution is very good. For one module only, we stay below 8.5%, and spatial resolution is also very good. You can see below, let's say, from 200 to 500 microns, and you can see essentially as a function of this distance, the dependence of the diffusion, let's say, which is dominating at high distance. Concerning the energy resolution, with 2 ARAM modules, we will go below 6%. This is a comparison between the present resolution, which is yes, very good, concerning compared to the bulk micromegas resolution, which is let's say much worse at small drift distances for at the moment obvious reasons. And one let's say weak point, but has to be improved, is the degrading of the resolution, the spatial resolution, for let's say as a function of the inclination of the track. But this can be improved by, let's say, a full fit, let's say, reconstruction of the track by fitting all the paths will function together. Okay, so in conclusion, I try to illustrate the status of the project related to the high-angle TPCs for the upgrade of an ND280. At CERN at the moment, we will move it to J-Park. The field cage is very thin and very, with high mechanical accuracy, starting to be built and assembled at CERN. Air detectors also had some, were studied in very detail. We are, let's say, foreseeing to build the detector at CERN this year and to move them next year in order to install and commission the two detectors at J-Park before summer 2023. And also the performances measured on the prototype are well in agreement with expectations. So thanks for your attention.
Thank you, Gian Maria. Are there questions? It's really lunchtime. I have one question. There is one. Yes.
I would just like to know how many years your story is telling us. I mean, when did you start the work, and how long did it take to build the detector?
So the project started in 2000, effectively, the design and the first prototype started in 2018. And of course, in the two pandemic years, we were stopped. Also, the company, it's some issues, so there were a lot of delays, especially last year. So, for instance, the first half cage was delayed by 8 months for the delivery, and this helped us to improve the design. In fact, was not time lost, but essentially we had 1 year of stop, let's say, and so yeah, so there is a huge delay concerning the final installation at J-Park, but there is nothing to do with this. In the meantime, also the accelerator is going to be improved there. Yeah.
Thank you.
No, I was wondering about the upgrade, just a general information. I mean, when the machine will come back up, and what will be the proton on target or the power that will be delivered?
Yeah, so at the moment the upgrade of the machine is let's say, foreseen to be completed by spring next year. There are already delays there, and the power should jump from 5 megawatts to 0.5 megawatts to 1.3. So it is more than a factor of 2. Probably it will be gradually increasing, and concerning the proton target, still we didn't receive from J-Park the planned proton on targets for the first phase of T2K, but in a few years and up to 2027, let's say the start of Hyper-K, we should reach 10 to the 10 to 1 as promised, let's say. And so this will be T2K phase 2, yeah.
Yes, last question, Mauro.
Okay, thank you. So you have shown a very good spatial resolution, even though you have quite large parts. This is given by the fact that you are having a quite large charge spread, because the resistivity is small, and you also use an algorithm that implies a pad response function. Yeah. So I have two questions on this. One is the resistivity is quite low, so if you have any problems with stability, so sparks, And the other question is related to the how much this method of reconstruction, the algorithm that you use, helps with respect to standard centroid or so, and how much it relies on this cluster size, because if it is small, it doesn't help.
Yeah, so concerning stability in time or aging, there is no problem of aging for neutrinos, of course, induced by radiation, but stability is tested since a long time on the single detectors, let's say, and it's very good. So we never experienced these charges. We had some issue with humidity. We had to wait a long time and to dry up the detectors. But after this phase is done, then there is no, we didn't experience issues. The issues were concerning stability in the production of the DLC foils, because from this Japanese company, anytime we have different resistivity for different batches. So we have to select small sizes. Also the yield is not so good. With uniform resistivity there, and so, but we develop in this 3 or more years, we developed some a protocol for this. Unfortunately, up to nowadays, there is no any batch is different from the previous one, and so this is an issue to us and to the production. Concerning the reconstruction of the, let's say, spatial reconstruction. So, yes, resistivity is low. It's a compromise, of course, resistance and capacitance. So there was a tuning again in this long period. We tested different combinations, and with the waveform reconstruction, we can do much better than we do with the path response function, because we are in fact also developing new algorithms. Somehow the path response function is something standard since 15 years, let's say. But it's not very good. It's very good for horizontal vertical tracks, given the geometry of the paths. But it's not very good for inclined tracks, inclined with respect to the in the transverse plane. At 45 degrees, it's completely bad. It's very bad. So we follow the standard approach, but we are moving to a global reconstruction, which implies a global fitting of each activated path waveform, and this is improving quite a lot. In fact, the resolution, especially for the inclined tracks. Yeah. Yes, I don't think I have many spare, but I don't think I can add some spare slides for this, which is very interesting. In fact, the difficulty there is that in order to fit the waveforms properly, you have to build a very detailed electrical model for the DLC, and this was a little bit complicated. Yeah, but and this is a very important ingredient. So we spent a lot of time in developing the infinite resistive chain and coupled with the infinite capacitor. Plane to let's say to modelize the DLC and electrical properties. Let's say this is the most critical part. Yeah, I indicated the thesis where this is discussed in some detail.
Okay, but you manage. Okay, thanks a lot. Other questions? I think we have to conclude here. It's already lunchtime. So let's thank the speaker again. Just a few words from me and Maxime. First of all, we would like to thank the organizing committee, and especially we would like to thank all speakers and poster presenters for this session that show a very major interest in the field of gas detector for this conference. And I think also Maxime would like to add some work about gaseous detector in the ECFA roadmap.
Yes, Beatrice, thank you very much. I think we were together with you delighted to receive so many contributions. I mean, unfortunately, only 10% of submitted abstracts were accepted as parallel session talks. So it shows in principle a great interest in the gaseous detector topic. And I think one of the points which you very nicely pointed out in the poster session summary was related to the point that most of the developments of the basic intrinsic performance of gaseous detector going along the lines of the ECFA detector R&D roadmap, which is very good, which is very natural. But of course, this very nice document, which was prepared by the ECFA detector R&D panel and Jan Shipsey, is very important for defining the future detector domain. And in relation to gaseous detector, one of the critical points, of course, is related to the implementation. And in addition to the basic detector performance, in particular, such things like supporting R&D facilities, engineering support, distributed R&D activities with centralized facilities. This is what needs to be integrated. So just to summarize, saying there is a huge interest in gas detectors, still remains, and we have to be very diligent in order to implement for the gaseous detector domain this roadmap to the benefit of the whole community. Thank you.
Thank you. Yes, we can close the other session and go for lunch. Hi, Maxime. See you. Bye-bye.
Thank you. Bye-bye.
Bye.